Sir, Ranjitappa, sir. Live streaming started, sir.
Okay, no problem.
Okay,
You can, if you have any video, you can on.
okay, sir.
Because we will wait for 5 minutes.
Okay, sir.
Convener will join actually. They are
Okay.
going to university to join.
Okay, sir.
Hello, Dr. Sanmay. Good morning.
Hi, good morning.
Yeah. Okay. So actually, Dr. Amit and Dr. Somojiti, who are the convener, they will be joined shortly, and we will start the program on as usual time.
Sure.
And I think we will have a first 2 lectures before lunch and after lunch 2 lectures in this symposium.
Thank you. I'm looking forward to it.
Yeah. So Professor Vineet and Balasubramaniam, you have to join. Hello, Professor Vineet.
Good morning. Good morning, Professor Ajit.
Good morning. So welcome to our one-day symposium. Convener Dr. Amit and Dr. Shomo, they are actually joining very soon because suddenly there was a power failure in the, I think, apartments, and they went to university, and they will be joining soon. So you can check your presentations is working or not.
Sure. Yeah. Please give me a moment. And also looks like I just even probably I have a looks like there's some the drilling going on around me. Hopefully, I do have some noise cancelling headphones if that happens. But maybe I hope you can hear me all right at this point in time.
Yeah, we can hear you. No problem.
Please give me one moment. I can share my screen and I'll, if required, I also have some noise cancelling headphones in case that comes up.
No, I think no noise that much is coming actually. Background noise, nothing is there.
Okay.
Good morning, all participants. So we will having 4 lecture in this one-day symposium and 2 lecture before lunch. And the lectures are made in such a way that there will be 1 hour lecture and then there will be discussion for 10-15 minutes. So if you have any questions for particular lecture, you can post in Q&A so that we will allow you to talk with, or we can take your question and ask to the expert. So please be with us, and any question you can post in Q&A section, not in the chat box section. Yeah, I think it is fine. We can see.
Okay.
Yeah, it is now in full screen.
You can tell me when I should start. I'll wait for your cue to start the talk.
Yes. Now you can stop sharing after checking, and then once they join, we will just start 1 or 2 minutes, and then we will introduce about the speakers and the one-day symposium. And I think from 10:05, 10:06, we can start your talk.
Sure.
Yeah, I think Dr. Somojit is joined. Hello, Dr. Somojit.
Yes. Hello.
Yeah. Good morning. So
Good morning.
everything went well. 2 speakers already joined, Professor Vineet and Professor Sanmay. And so we already checked their PPT presentation file, so it's fine. And once Amit joined, we can start the.
Yeah, Amit is just he came with me and he's joined. Just give us a second.
There in our.
Hello.
Yeah, there he is.
Amit.
Yeah. Can you hear me?
Yes.
Okay.
Speaker already joined. We have checked the all the presentation, so everything fine.
Okay. Very good. Okay. Maybe we can start. So already, or should I wait for 1 more minute?
Yeah, I think you can talk with first speaker. Hello, Amit. You just talk. Vineet. Hello, Vineet. Professor Vineet.
Yes.
Yeah.
Hello.
Here.
Yeah. Hi. This is Dr. Amit. Thanks for accepting our invitation. Hello. Can you hear me?
Yes.
Hello?
Yes.
Okay.
Yes, I can hear. Yeah. Please. Yeah. We can start.
Okay. So thanks for accepting the invitation, and we are really looking forward to your talk. And our HOD sir will tell you our activities in the department, so you will have idea of our departmental works. But we will also really look forward to have you on campus someday and listen to you and talk to you physically also. Okay.
Sure. Thank you very much for having me here.
Yeah. Okay. So maybe let's start. Okay. So let's start.
Yes. Go ahead.
Okay. Good morning, everyone. Very good morning from SRM University, AP, Andhra Pradesh. So we are very happy to see you all. So this is a one-day symposium, applications of machine learning methods in physics. So what we are going to have is that you might have seen the brochure. So we will have 2 talks in the morning session and 2 talks in the afternoon session. And morning session, we have Professor Vinit, who will talk about explainable deep learning methods and overview trends and challenges. And then from 11:30, we will have another talk from by Dr. Girish Verma from IIIT Hyderabad, and he will also talk about deep generative methods and applications. So after that, in the second half, we will have seminars on application side. So first, it will be Dr. Sanmay. He will talk about the applications of deep learning methods in particle physics. And then in the last session, we will have the application of machine learning methods, but now in the area of statistical physics, especially on crystals, plastic deformations. So hope you will all enjoy. And before I start, just quick comment that you can use the Q&A option to ask your question during the talks if you have. And also there is an option to interact with the speaker directly at the end of his talk. That's also possible. And each talk will be of 1 hour and followed by half an hour of discussion. Okay. So that's the format that we will be following. And this talk is also recorded and live telecasted on YouTube. So you can also share the link with your friends so that they can also join the YouTube session there. So before we start the seminar, I would like to request Professor Ranjit Thapa, our HOD, to share a few words and welcome the participants. Over to you, Professor Thapa.
Yes. Thank you, Dr. Amit and Dr. Somojyoti, to organize such a nice emerging topic of physics, where actually we need the help of machine learning to solve some mega problem. So I welcome all the participants for this one-day symposium, applications of machine learning methods in physics. And the 4 speakers, I want to really welcome them. Professor Vinit from IIT Madras, Professor Girish from IIT Hyderabad, and then Dr. Sanmay from University of Tokyo, Japan, and Professor Lassi Laursen from Tampere University, Finland. So about our department, we are just 4-year-old university. And just in last December, this December and last August, we have first batch who has come out. And so in average, we are around 2.5 years or 3 years old department of physics. But I am happy to say that our each faculty, we have 11 faculty, and they are associated with a funded project. So that means all of the faculties are working in the funded project. So this is really proud for us. And also in the last couple of years, we have published 5 patents from our Department of Physics, and we have reached more than 110 quality publications with an average impact factor of 5.2, and almost 70% of our publications are in Q1 journals. So which indicates that our department is very vibrant in research. And particularly, we are also strong in teaching, and we are also teaching BTech students, BSc students, and we are going to start from this year MSc. And we have around 28 PhD students, and also we are taking more and more PhD students. The next round is in January 8th. So with this, I want to thank the organizer, particularly Dr. Amit and Dr. Somojyoti. And there is overwhelming response. More than 700 registrations are there, and I am sure that always there will be a crowd of 200 in this, and there will be also a link on YouTube. So with this, I want to request Amit to go ahead and introduce the speaker, and then we can start the lecture. Thank you, Amit.
Thank you, Professor Ranjit. So maybe we can start our seminar now. So let me introduce our speaker. The first speaker is Professor Vinit N. Balasubramanian. So he is an associate professor in the Department of Computer Science and Engineering IIT Hyderabad and also the head of the Department of Artificial Intelligence at IIT Hyderabad. His research interests lie at the intersection of theory and applications of machine learning, especially with a focus on computer vision. So in that sense, it's a truly interdisciplinary, and he has a strong interest in mathematical fundamentals and, of course, real life applications. So he has a very vibrant group at IIT Hyderabad carrying out impactful research in different areas of deep learning, machine learning, computer vision, and of course, guided with applications in the context of real world use. He is one of the leading scientists in this field. He has published several papers and reviewed several articles, and many research articles are published in peer-reviewed journals, also in several conferences, prestigious conferences like ICML, CVPR, IEEE, etc. And he also received several awards, both as a teacher and as well as researcher. One of the outstanding reviewer he has been for ICLR 2021. So with that very brief introduction, I would like to request Professor Bineet to start his seminar that's on explainable deep learning. Over to you, Professor Bineet.
Thank you very much for the very kind words and the kind introduction and the invitation for presenting at this venue. Please give me one moment. Let me just share my screen again and we can get started. Okay, I assume my screen is visible?
Yeah, it's visible. Yes.
Okay, great.
Yeah.
Thank you.
Thank you.
Yeah, thank you and good morning to everybody and for attending the session on a Saturday on a morning. Yeah, a good number of people joining. Thank you for joining in and participating in this. I know probably my talk and perhaps my background is a bit of a misfit maybe. I mean, I'm not a physicist, so bear with me on that. But I think there are increasing applications of machine learning and deep learning in basic science in general, in physics in particular. And hopefully this talk will provide some new light in directions of applying deep learning to physics. And I also believe that when one talks about applying machine learning and deep learning to basic science in general, science subjects in general, explainability is extremely important. Knowing why a decision was made is the fundamental foundation stone of science, right? So the question of why is what really makes scientists tick. So hopefully the notion of explainability in machine learning and deep learning will become clearer, and the scope for it in these kinds of applications will also be clearer at the end of this talk. Okay. So with that, let me actually get into the talk itself. So the first question perhaps is to ask is, why is anybody and everybody talking about explainability itself? I mean, all of us use machine learning in several applications. I'm quite sure all of you, be it your spam filter on your emails or your face detection module on your Facebook or your Google Translate or your Apple Siri, there's machine learning and deep learning being used by you on an everyday basis, or even your, say, Amazon product recommendation system. I think it's all machine learning that's driving these products around the world today. So if that be the case, we seem to be successful, machine learning seems to be successful, then why complicate issues? Why do we talk about explainability? So let me probably start by contextualizing this so you get a sense of why this problem is important in today's times. By the way, I should just say that I think there is some noise around me. If you think the noise is too hard on you, please let me know. I have some noise cancelling headphones and I'll get onto it if it becomes required. Okay, please feel free to let me know. So the European Union actually passed a regulation called the GDPR, General Data Protection Regulation. This was 2-3 years ago, which states that a business using personal data for automated processing must be able to explain how the system makes decisions. Okay, so the article and the recital are right here. So why does this affect us, right? So someone could say, okay, this is European Union, a first world problem. Why do we really need to worry about a problem such as this, right? Let me explain that to you. Let's assume now that there is a bank in Germany that's using machine learning to decide whether a customer should get a loan or not. I mean, today it's very common to use machine learning to decide whether a customer should have a loan approved or otherwise. And it's very likely that for that software, for that German bank, one of the Indian companies, say an Infosys or a TCS, could be developing the software. So tomorrow, if a customer is denied a loan, according to the GDPR Act, the customer can go back to the bank and ask, if you used machine learning to make my decision, can you tell me why you made the decision to decline my loan? Okay, this is enabled by the GDPR Act in the European Union, European Union's GDPR regulation. So which means the bank is now going to come back to the Indian company or say an Infosys and then ask, can your software now tell me how it arrived at this particular decision? Right? So straight away there, we have to ensure that whenever we deploy machine learning models, the models can also explain its decision should a customer want to know the reason. Okay, so this is just not a European Union problem. US, in fact, has multiple such acts. One of them is written here called the Algorithmic Accountability Act, which requires companies to provide an assessment of risks posed by an automated decision system to privacy or security and the risks that contribute to inaccurate, unfair, biased, or discriminatory decisions impacting consumers. Even in India, we have what is known as the responsible AI. Niti Aayog has been working on a responsible AI strategy for the last couple of years. The document is publicly available if you search on the web. And one of the important aspects of responsible AI is trustworthy and explainable AI. Right? So that's a very important aspect of implementing AI even in the Indian context. Even more fundamentally, there is what is known as the right to explanation. Right? So in fact, you can go to the Wikipedia article and see what the right to explanation means. This is a very old right. It's just that it's never spoken about in the context of AI and machine learning. People have spoken about this in the context of, say, finding your credit scores or other kind of applications. But now this right is becoming coming to the forefront, considering the significant use of AI and machine learning technologies around the world. So what are people doing for this, right? So what is the community doing for this? What is the technology community doing for this? So obviously there's a lot of talk, a lot of effort going on in this space. So the entire effort is broadly categorized into what is known as FATE. FATE stands for fairness, accountability, transparency, and ethics. I think all of these aspects are important when you talk about responsible AI or even explainable AI to a large extent. And ACM, which is one of the foremost bodies in computing, Association for Computing Machinery, which also awards the Turing Prize. So they have launched a bunch of different conferences, including one known as FACT, which stands for Fairness, Accountability, and Transparency. There's another conference called AI, Ethics, and Society. There's another conference called Compass, which is a little broader. All of these conferences allow technologists and social scientists to come congregate in the same venue and discuss these issues when we talk about deploying AI. So there's a lot of work in this space over the last few years, and I'll try to touch upon them over the rest of this particular talk. So for the rest of today's talk, I'll do my best to keep a tab of time. The rest of today's talk, what I'll do is I'll continue to give an overview of what explainability means, how is explainability being perceived in machine learning, so on and so forth. Then I'll talk about an important aspect of explainability, which is known as attribution. Attribution simply means how much does an input variable attribute towards an output, which is explainability essentially. To find out which aspect of the input contributed to a model prediction is essentially how explainability can be useful. So I'll talk about a few methods in that direction. Then I'll later talk about some of our ongoing work in this space briefly. And I'll conclude with some open problems and challenges that hopefully will be of relevance to all of you. So this is going to be a semi-technical talk. I'm going to assume some basic background in machine learning and deep learning. Please bear with me or feel free to ask questions if any of it is not clear. I'm going to assume some intermediate level expertise, but hopefully I'll try to keep it simple to so a broader audience can follow what I'm trying to speak. One disclaimer before I go forward is the space of explainable AI in general is very broad today. The reason it's broad because the notion of explainability is very subjective. And what somebody perceives as explainability, even for you and me, how somebody explains something to you may be different from how somebody explains something to me. Right? So the notion of explainability is very, very subjective. So which means there are numerous names and faces of it over the last few years. So it's essentially a multidisciplinary field, because it involves AI and computer vision, NLP, speech, of course. It involves human-computer interaction. It involves social science, because you need to understand what the user expects while talking about explainable decisions. I'm not going to call this as a very exhaustive talk. As I said, there's a lot of work in this space. but I'll try to cover an overview of key methods that have emerged over the last few years. Okay, so as Dr. Amit mentioned, a lot of the work that we do in my group here at IIT Hyderabad is on computer vision. So I may have a slight bias towards computer vision in my examples and methods that I talk about, but most of it is relevant more broadly to other areas of deep learning also. So, but once again, I'll be happy to take any of these questions towards the end. Okay, so let's step in a little deeper. So if one had to characterize machine learning applications today, right? So let's look at all the applications that we successfully use today. I talked about Google Translate. I talked about Amazon's product recommendation. I talked about the spam filter that we use. Maybe there's a tweet sentiment predictor that Twitter uses to probably decide which tweet should be pulled down. So all of these, let's try to abstract out what kind of questions are these models answering, right? So the kind of questions could be, what is the product relevant to the user? What is the sentiment of this tweet? What are the objects in this image? And if you look at the high-level abstraction of all the questions that machine learning methods today answer, they are, what is X? Right? X could vary based on what field you use it in. If you're using it in biology, a person takes a camera to the Amazon forests and uses the camera to look at a new species of insect, and they want to see if it has been discovered before. The question is, what is this insect? Right? What is X? That's essentially the question that all these machine learning models are typically used for. And if you also observe carefully, in terms of where machine learning is successful today, the cost of a bad decision in most of these applications is low. Okay, you get a bad product recommendation, a bad movie recommendation, you lose a max of 500 rupees, maybe 3 hours of your time, you don't lose your life. Generally, people consider accuracy to be all important when they train machine learning models. A certain method gets 90% accuracy, someone else wants to get 92% accuracy so that they can do better on that particular application. This leads to a very one-dimensional approach to the problem, because all you're worried about is just optimizing one particular criterion, which is accuracy, and the why almost doesn't matter in all of these applications that we use it today. Okay, so it really doesn't matter. Let's then see what is it that's missing, right? So, okay, this maybe many of you understand, but then what is missing? What is missing is, or what we need to fulfill going forward is, how can machine learning be used in more complex real world systems? Risk sensitive systems like medical diagnosis, financial modeling and prediction, or safety critical systems like cockpit of a flying aeroplane. So these are risk sensitive systems. What differentiates these from the previous slides applications? The cost of a bad decision in these applications can be very high. So the cost of a bad decision here could be lives, many lives, loss of property, could be many such things like this. So all through the entire COVID phase, the pandemic that we've all been going through the last 1.5 years, there was no hospital that said, we don't want to interact with the patient. When you come to the patient, we'll have a robot. Okay, we'll use a machine learning algorithm to diagnose whether you should be admitted or not, and then turn out patients, right? So nobody did that. Why? Because the cost of a bad decision, the cost of a mistake in these kinds of settings can be very, very high. Accuracy may not be the only objective. Yes, I may have a machine learning model that is 95% accurate, and I deploy it at the entrance of the hospital, right? But then if a patient goes in there, the patient is going to ask, what if I'm in that 5% where the model makes a mistake? I want somebody to explain to me why the decision was made. So that leads to a need for a multidimensional perspective, right? So it's not only about accuracy here, it's also about accuracy and something more, which is the explanation, which is the rationale, right? So today it's very common that if you visit a healthcare facility and a doctor says something, say that do this, everyone wants to know, why is this the case, right? What could be the implications? We want to know all of those things. We want that multidimensional perspective before making risk sensitive decisions. It's not just one perspective we consider. How do you bring this into automated decision making is what explainable AI is at least about at this point in time. So then one question is, don't existing machine learning models already do it? Can't you take something from them that gives us a score or something that relates to explainability? People have studied this, and it happens that if you look at existing machine learning methods, the most interpretable ones are the ones like linear regression and decision trees. which unfortunately are not the most accurate when it comes to real world data sets. On the other hand, you have models like neural networks and support vector machines, which are perhaps the most accurate when it comes to deployment, but they're not the most interpretable when it comes to practice. So what do we really want? We ideally want to push this towards the top right. We want tomorrow to be about pushing these machine learning methods towards the top right, where models are both highly accurate and highly interpretable. This, unfortunately, is still a journey. We're not there yet. There are a few methods at this point in time, but that's the focus of building machine learning models that are inherently interpretable or explainable. So is this really required? I mean, what kind of applications? As I already mentioned, there are many applications that run well without explainability. Amazon's product recommendation or Google Translate, or one mistake here and there isn't really going to hurt you. It's okay, right? Google Maps, we all know makes a lot of mistakes, but it's okay. I mean, you probably lose 10-15 minutes in the last mile figuring out where a house is or where a shop is, but we managed to figure it out. It's okay. The mistake doesn't really cost a life or many lives. Are there really applications that need XAI? Plenty of them. Right? So if you look at space and aircraft applications, if you look at general infrastructure applications, it's very common today to use machine learning and even say drone footage to go inspect infrastructure across a country or across a region. Be it railway tracks, be it bridges. Are there cracks in the railway tracks? Are there cracks on a bridge? Is today talked about as being as a good application for machine learning to detect these kinds of things. So this is a high risk application. If a machine learning model makes a mistake on a bridge, on a railway track, it could lead to loss of many lives and property over the years. Insurance, another application space. Financial modeling, another application space. And biometrics. Right? So in fact, there has been articles in the last few months, in fact, where there have been people who have been arrested for wrong reasons, just because there was a biometric software which used machine learning essentially that used to profile people and give them scores, right, which was making a mistake. So knowing why it made a mistake or what it used to arrive at a decision can be very, very useful in reversing these kinds of decisions in practice. So whom is explainability for, right? Is it just for somebody who owns? Is it somebody for somebody in the hospital? Is it for a consumer like you and me? Is it for an IT operations person? Whom is explainability really for? So if you look at it, it can mean different things to different people. And that's actually the problem, right? So which is why it's not simple to come up with generic solutions for explainability across applications. And it may need to be fine-tuned for a given application depending on who is using that particular application. If it's a business owner, the business owner may want explainability to know whether he or she can trust the decisions of an AI model. A customer support agent, let's say a particular website has a chat bot based on which a customer interacts. The customer support agent may need explainability to understand how to answer a particular customer complaint, right? So you probably know what is the outcome or what is the customer trying to say, but now how do you answer it, or what needs to be resolved to answer the customer complaint may need explainability. For an IT ops person, it may need, how do I monitor and debug this model? So there is a model that's deployed, a machine learning model. It's going wrong. Now the IT ops person may want to know, how do I debug this? Explainability may be useful to understand what is going wrong inside the model. A data scientist may want to know what is going wrong in the model so that they can build better models in the future. And internal audit regulators and policymakers may want to know whether the decisions made by these AI systems are fair. They don't have, for example, I talked about machine learning used for deciding whether a customer should get a loan or not. Imagine that a software is used for many years for giving this, and once explainability comes, we find out that a particular model was using gender to decide whether a person should get a loan or not. This is clearly unfair, right? So to even understand these things, explainability may be very useful to debug, find out whether a model is fair, and address these bias issues over time. So then what do we really want, right? So what are we looking at in future in terms of an end-to-end explainable AI system? This is just one hypothesis. I don't think this needs to be the only one. There could be multiple ways in which explainability could be built into machine learning and deep learning models in the future. But here is one, right? So if you have an image and a machine learning or a deep learning model predicts this to be a fish, this is what is known as traditional supervised learning, which is where most applications today lie. The step one is where most applications in machine learning today lie. So now what we're talking about is, what if a human, which is denoted by H here, chooses to ask why? Why do you say it's a fish? Now the computer gives an image where it highlights which parts were focused on while making the decision. So green regions argue for fish, red regions push for dog. There is more green, hence it must be a fish. So this is commonly done today. This is at least one of the methods people use to understand how a model works, especially on images, is to look at which part of the image did a model look at while making a decision. And if that makes sense, you move on. Right? But clearly this can have its own problems. Now a human could say, okay, seems like it might just be recognizing some unknown texture in the background. Which training examples were most influential for the prediction? Can you share that? Maybe that will give some more useful inputs to the human making the decision. Now the computer retrieves a couple of images which are closest to this particular image and says that these were the closest images, these belong to fish, and hence I think this image could be a fish too. Okay, so I'm giving you a very simplistic example of fish. This example is borrowed from this paper down here, but you could imagine a similar thing for a COVID chest X-ray, right? So you could imagine that this was a COVID chest X-ray, and there was a machine learning model that was trying to score the X-ray based on some machine learning model internally, and then give a score of what could be the risk of COVID or a CORAD score or something like that. Right? And now based on this, the human now asks, okay, I'm still not convinced. What happens if the background anemones are removed? Okay, so then only the fish remains, the background goes, and the computer says, I still predict fish because of these green superpixels. Now, after this iteration between the human and the computer, now a human may feel convinced that the model is saying the right thing, right? So especially in risk-sensitive applications, a human may want to ask these questions before making up his or her mind and using this decision as an outcome to make a treatment or to make a decision. Okay, this is what we're hoping for in the future. Unfortunately, we are not there yet, but this is a journey that we are going through at this point in time. So is that the only kind of work that's being done around the world today? Not really. Most of the work in explainable machine learning and deep learning started around 2015 or so, when DARPA, which is the Defense Advanced Research Project Agency in the US, started an initiative on explainable AI in 2015. They started, they thought that this was very useful for defense and security scenarios, and they launched a lot of funding opportunities in this space. That is what was the initial catalyst for the growth of explainability. But over the last 5-6 years, there has been tremendous growth of the field from multiple perspectives. From a core machine learning standpoint, people try to study which features are responsible for classification. From a computer vision standpoint, people try to understand which features are responsible for classification in an image. From a multi-agent system perspective, people try to understand which agent strategy and plan was used for a particular scenario, which player contributes the most, say in a game theory perspective or in a robotics perspective, which decisions, combination of multimodal decisions led to a particular action by a robot. In NLP, it could be which entity is responsible for classification, so on and so forth. As you can see, depending on which application the problem is being used, is considering, explainability could mean different things for each of these applications. So one way of summarizing, right? I'll take a couple of slides to just summarize most of the work that's been going around today. So there's also some debate about the difference between interpretability and explainability. I think these days, both of these are used interchangeably. And personally, even I would think it's very hard to distinguish one from the other. So even the notion of explainability itself being subjective, it's very hard to make distinctions. But the current general understanding is that interpretability is about if you had a machine learning or a deep learning model make a decision for you, which input feature or set of features was responsible to make a particular decision on a data is interpretability. Explainability is generally considered as the transparency inside the model. When a model made a decision, can you look into the model and say what really made the model make this decision? So that's what is denoted as explainability at this point in time. There's a very subtle difference, but this is the common understanding. This is the common convention people use today. So within this broad space, there are interpretable models and explainable models. Interpretable models are where you can give a global importance, like linear regression, where you get a weight for every attribute, which is a global interpretable model. I'll also talk about this in the next couple of slides. Or a local, where for every data point, you give a different weightage for which feature was responsible for a particular prediction. Within explainable methods, explanation methods, there are attribution methods, actionable explanations, so on and so forth, some of which I'll talk about over the next few slides. Even more broadly speaking, existing methods for explainability can be broadly classified into post hoc versus anti hoc. Post hoc is the more common one, where explainability is added as a layer on top of the machine learning classifier. Okay, there's already a machine learning classifier. So we add a layer of explainability to it using some other kind of analysis, right? So which means the machine learning model is already built and deployed. We are going to do some post-processing to find out explanations. On the other hand, anti-hoc models are where explainability is ingrained while training the model itself. An example for this would be, say, linear regression or decision trees, where while training the model itself, you deal with how you can interpret your prediction in these kinds of approaches. Then there are also what are known as model agnostic versus model dependent approaches. As the name states, model agnostic is where the explanation method does not depend on what machine learning method you use, and model dependent is where the explainability method depends on what machine learning method you use. Even there is also the notion of global versus local. Global, as I already mentioned, is where the explanation is across a population. So you try to say that across the people in, say, Hyderabad or Amaravati or whichever place you belong to, you say that this is the attribute or the feature that's leading to this prediction, right? So that's a global explanation. On the other hand, a local explanation is for every data point or, say, every patient. You try to explain the decision based on analysis of the features of that particular data point. Okay, those are some broad categorizations of explanation methods and their use today. So one important thing to talk about before we go into the methods itself is how do you really evaluate explainability, right? So explainability is not something too objective, it can be subjective. So how do you evaluate any explainable method in general becomes a general question to answer. So there are a few different ways in which people do it. I think they are debatable, but this is what can be done given what we have at this point in time. One of the common approaches is once an explainability methods picks a set of K features or K input attributes that may be responsible for a particular outcome. So now to check whether that really are the right set of features, one thing that you could do is now perturb those top K features and see if the prediction changes significantly. If it does, you know that your capturing of those K attributes is correct, right? Because changing them is leading to a huge change in the decision. If by changing them, there was no change in the decision, you're probably right that they don't contribute much to the outcome. Okay, this is measured using a metric called the area under perturbation curve. So where you perturb a little bit and see the change in a decision. A more common way of evaluating explainability is use humans in the pipeline. Right? So you present the decisions to a set of humans and then ask the humans a set of questions to see whether this decision makes sense to you, the explanation for this decision makes sense to you, does it help solve your problem? Based on whatever application you're solving, you may come up with a few questions and then ask the user and then report those as user studies and try to understand how explainability works in these kinds of settings. With a human role-based evaluation, there are multiple kinds of metrics that have been proposed. The usefulness of the explainability, the relevance of explainability, the coherence with prior belief, how these are composed, the uncertainty, so on and so forth. Right? I'm not going to go into each of these, but I do have links under each of these slides which you can look at if you want to know more about each of these aspects. There is also a different way of looking at explainability itself. I think I talked about this briefly in one of the slides earlier, is instead of trying to look at a particular part of an image or a feature in an image, a feature of a data sample to find out which of them was most responsible for an outcome, you could also give explanations in terms of examples. Right? For example, if somebody says, why did you call that a cat? One is I could explain saying I'm calling that a cat because I can see whiskers, a tail, 4 legs, it has a furry body, furry coat, so on and so forth. So I could do that. The other thing I could do is to see, look at those two things. Somebody already told me that they are cats and that they look similar to this. Hence, this must be a cat. You can also give explanations by example. Okay, so then you can also evaluate them in a more objective way because you may already know what those previous examples belong to. Okay, this is other way of studying explainability in general. Okay, there have been efforts which have studied this in more detail. Here is a paper. I'm not going to go into it in too much detail, but they considered data from different domains. They considered different objectives ranging from finance to facial recognition to healthcare. And they tried to look at who are the stakeholders and what kind of evaluation criteria was used in each of these work. And they presented this as a survey, which is something that could be useful to people, other people that are trying to use similar methods. Okay, so hopefully that gave you some kind of an overview, the need for explainability, what is being done, and some idea of how to evaluate it. Let me spend perhaps the next 10 to 15 minutes or so on a few different methods that people have proposed over the years for explainability, in specific for deep learning. Right? So there are other machine learning methods too, but deep learning is in a sense the flavor of the day. So we'll focus on deep learning and what kind of explainability methods have been proposed for this over the years. As I already mentioned, you have interpretability and explainability. So within this, you see that there is one notion of explainability here, which are called attribution methods, which is what we're going to focus on over the next few slides. What attribution methods try to do is find the attribution of an input towards an output. Okay, I hope that part is clear. So remember, whatever data it is, be it images, be it text. For those of you from physics, it could be a TEM image, or it could be an image that's coming out, or some signal that's coming out from a far out star. Whatever data it is, data is made of certain dimensions. And those dimensions are what we call as features or attributes. And in machine learning, you generally try to predict an outcome. Attribution is how much you associate each of those features in the data towards the prediction of a certain output in a certain data sample. Okay, that's what we refer to as attribution. And we'll see a few methods in that scenario over the next few slides. One of the earliest work in this space was called LIME. LIME stands for Local Interpretable Model Agnostic Explanations. It's published in 2016, extremely popular. It's used today by many companies and many of their products, but many of you may not know it, but you're probably using a product that already has LIME deployed in it at this point in time. So I'll talk about what LIME means. But before I give the method itself, I'll talk about what was their motivation to do this work, which is pretty interesting, I think. So they studied, among many different data sets that they studied, they also studied a text-based data set known as 20 news groups. 20 news groups is a data set which has many emails, a part of a distribution list, that divides each email into a category among 20 different categories. The categories could be sports, politics, atheism, Christianity, so on and so forth. Right? There are about 20 categories. And each email was categorized as belonging to one of these areas. So there was a random forest, which is considered a fairly strong machine learning model, which was trained on this data set. And it got 92% accuracy, test accuracy, which is considered a pretty good accuracy for such a data set. So the model was working well. It's something that's probably used for such a data set. When they studied this model more carefully, they found that here is an example of one of the emails in the data set, one of the emails in the distribution list. And the model correctly predicts this post as belonging to the atheism class. It's a correct prediction. Okay, that was the correct category for this particular email. But using their method, when they try to understand the attribution of which words in this email attributed most for this post to be called as belonging to atheism, they found that the words were edu, NNTP, posting, host, there, have, and have. None of this has anything to do with atheism. The only reason the model picked on these to give the outcome as atheism is that in most of the emails with atheism, these words occurred and these words did not occur in the posts relating to Christianity. That's it. These spurious correlations in the data set, we're making the model believe that whenever there's a word called NNTP post, there have an edu, this post must belong to Atheism. This does not really make sense in practice, especially in risk-sensitive applications. Okay, so that's what they try to motivate their work with. The way their method actually works is, here is an example. I'll try to speak very intuitively, not go into the math at this time. But if you have an image, let's assume that the machine learning model, this is a post hoc method, which means you do this after training a machine learning model. So if a model already predicts that the probability of such an image belonging to the tree frog is 0.54, okay, then now our objective is to find out which part of the image did the model look at while making this prediction, which is what we refer to as attribution. Which pixels or which regions in the image maximally attributed towards calling this a tree frog. So we see here that what they do now is they perturb this input image. So you can see that this is a perturbed instance, this is a perturbed instance, this is a perturbed instance. And they now try to see with the perturbed instance, what would be the prediction of a tree frog. You see here that if they perturb and occlude different parts of the image but the face, the probability is 0.85. If they occlude the face and keep other parts of the image, the probability drops down to 10 power minus 5, and so on and so forth. Now they build a locally weighted regression model, and which tells them that the face had the highest weightage in making a decision on this image being a tree frog. Okay, this becomes a method now to find out what aspect of the image the model relied on while making this decision of this image belonging to a tree frog class. Okay, so this method is known as LIME. So the perturbations in this case, when you use images, are by occluding different parts of the image. But if it was any other kind of data, you just had some numerical data, you can add some Gaussian noise to it, you can add any other noise to it and perturb the data and see how the outcome changes. Build a regression model. The regression model gives you weights of different data points towards the outcome, and that tells you which part of the input was actually maximally attributed towards a certain outcome. There's another method, popular method called LRP. LRP stands for Layerwise Relevance Propagation. So this is quite popular on as on the website called heatmapping.org. So this website has the code for this method, which is again used by many researchers and even industry practitioners around the world. What Layerwise Relevance Propagation tries to do is it talks about it in the context of a neural network and tries to measure the relevance of every node in a neural network towards the outcome. How does it do it? You can use the gradient of the neural network itself to get a measure of how much the last few nodes contribute towards the output. And now you can propagate that relevance back to the previous layer, then back to the previous layer, so on and so forth. And they have a simple formula for doing this, where A is the output of a certain layer's neurons, and W are the weights connecting those two layers for a layer being studied in a given setting. So in fact, they have a few different variations of such formula. Depending on different layers, they have some slight changes in these formulas. And this is used to compute the relevance of every node in a neural network or every neuron in a neural network towards the outcome. And because they do it for every neuron, you can also do it for the input neuron and hence get the relevance of an input attribute towards an output for a given data sample. Okay, this is what LRP tries to do. There's also another method called Deep Lift. Deep Lift was published in 2017. What Deep Lift tries to do is the essential notion of attribution can be related to a gradient. Right? Remember, the first principle's definition of a gradient is you have an input, you change it slightly and see how much the other variable changes. That's essentially the first principle definition of a derivative, right? So that's the same thing that you could use here to get attribution. I can find out if I change the input, a certain input by a certain amount, how much does the output change by? That tells me how much an input is responsible for a certain output. Okay, that's what I want to know in this particular case. But this particular work called Deep Lift, what it says is that the notion of gradient can be very sensitive to which region of the input you're trying to evaluate on. Right? So if a value is certain, certain value, an infinitesimally small change in that vicinity may either spark a large change in the output or may not. But if the same input becomes a different value, now an infinitesimally small change can have a large change in the output. So it can be very sensitive to how and where you're measuring it. So this particular method called Deep Lift, what it states is, let's not use the notion of gradient. Let's slightly change it. Instead of considering a small change in an input, let's measure the change in input with respect to some reference value. We have a reference value for an input. We know the corresponding reference output for that reference input value. You can get that by propagating the input through a machine learning model or a neural network model. Now you see, if you now change the input from that reference value by a certain amount, how much does the output change from that reference value by a certain amount? Right? Why does this make sense? Suppose I'm trying to find out what is the attribution of blood pressure towards predicting the risk of COVID. We all know that there is a standard BP, 120 by 80, right? So now I can always measure the attribution of blood pressure towards risk of COVID with respect to the reference value 120 by 80, right? So because we all know that's reference value for blood pressure, so you don't need to worry about gradient in an infinitesimally small neighborhood of a value that you have. You can do it with respect to a reference value for a given application. This is the main difference that this method introduces. It's called deep lift. Otherwise, the computations are very similar to gradients, but using the notion of a reference value. Of course, here they also use a few different rules, the way in which the actual contribution of an input is computed in practice. Okay, so then looking at images, it's very common for images to use gradient-based methods to compute how relevant an input is towards the output. A typical neural network has an error function or a loss function that's defined at the end, based on which you train the neural network. And the way a gradient is computed while training a neural network is to compute the gradient of the error function with respect to the parameters of that model, the weights of the neural network. Instead of computing the gradient of the loss with respect to weights, you can also compute the gradient of the loss with respect to the input. Simple chain rule, right? So you can just do that. And that now gives you a sense of attribution of an input towards an output. A very popular method that's used in this context is known as integrated gradients. In fact, this is a seminal work and one of the most popular methods people use today to find attribution. Integrated gradients states that because gradients in general can be very sensitive, okay, based on what is the input. If the input is there, a small change in the vicinity of the input could or may not lead to a large change in the output, depending on how you're measuring it, depending on what are the values at that given point in time. To avoid that sensitivity, integrated gradients proposes a path-based gradient approach to measure attribution. The path-based gradient simply states that if you have an image, you first take a black image and then gradually interpolate between the black image and the given image, right? So imagine you're given whatever image you have a black image. Now you gradually interpolate between the black image and the given image. So depending on how many interpolations you create, you'll have a set of images. Now compute the gradient of an input on the output for each of these images that you create on the path and average all of them to get an integrated gradient. Okay, this is what is proposed. They show that such a gradient is more robust to small changes in the input rather than be too sensitive to input values. In fact, they go ahead and show that this kind of an approach of using a integrated gradient satisfies certain axioms of attribution, such as completeness, sensitivity, implementation invariance, symmetry preservation, so on and so forth. There's also a method called SmoothGrad. As you can see, one thing that should be clear through all the discussions right now is the notion of gradient between the input and the output is very closely related to attribution, which is closely related to explainability. Okay, that's what we are trying to drive at here. SmoothGrad is another approach where they try to address this sensitivity issue of the gradient by simply adding noise to an input and taking the average of attributions that you get across several noisy inputs. The hope is if you do that, you'll be more robust in terms of the gradient and the attribution that you compute through this procedure. While all of these methods that we spoke about use gradient in some form or the other, right? So probably some slight adaptations of the gradient, but largely uses the notion of gradient. There is a completely different way of measuring attribution too, which are based on what are known as Shapley values. Shapley values is a game theoretic concept developed by a person called Lloyd Shapley. In fact, he won the Turing Award for this work early in the last decade, 2011 or somewhere there, if I'm right. So Shapley values, what they try to compute is if you had any coalition, it's a game theoretic concept. Imagine you have a football game and you now want to find out how much Ronaldo is now contributing to Manchester United. Let's say that's what you want to find out. Right? So which is in a sense attribution, right? So I want to find out which player is contributing most to the success or failure of Manchester United. And let's say for the moment, I want to study Cristiano Ronaldo's contribution to Manchester United's success or failure in recent times. So what I can do now is I use what Shapley values suggest is to use a formula such as this. What it says is you have something known as a value function. That is something that you define for different applications differently. Say for football, it could be how many goals scored versus goals scored against, for instance. So you define the value function and now see for every team possible, right? You consider a team without Ronaldo and then add Ronaldo to that team and see how the value function changes. And you do this for every possible coalition without Ronaldo. You have V of S, we have V of S union I, which is the set with the current player that we're considering. And you see the differences between these two across all possible coalitions, across all possible teams, right? Whether the team size be 2, 3. If you have a team size of 2, if you add Ronaldo to it, how well do they do? Right? If you have a team size of 10, if you add Ronaldo to it, how well do they do? And then you average it all out across all the possible combinations. This is is how Shapley value is measured. And how Shapley value is connected to explainability is now you could consider this value function to be a gradient-based function that computes the importance of an attribute towards the outcome. And now you try to see if I have all my input features and now I add one input feature to it, how much does the decision change because of this new input feature that I added? Okay, that's how Shapley values can be used in explainability. Okay, this was first introduced in 2017. And the value function that they used was actually the value function based on deep lift, which uses a varied notion of gradient to get it. But there have been more recent work in the last 2-3 years on trying to adapt Shapley values more deeply to get a sense of attributing an input towards an output. Okay, so I know I have about 10 minutes. So in those 10 minutes, I'll quickly talk about some of our ongoing work in this space, and I'll then perhaps just conclude with some open problems and challenges, and then take any questions that any of you may have. So we have been working on this space for the last few years in my group at IIT Hyderabad. So we've been looking at it from multiple perspectives. We have been looking at trying to give explanations from a causal perspective. So causal perspective, I'll explain this in a moment. So let's assume again that we are trying to predict, say, the risk of a heart attack for a patient that goes to a hospital using a machine learning model. And I'm just giving a few examples. You could extrapolate it to any other example too. Right? So it's possible that for all the data that you may have in a data set based on which you're building a machine learning model, whenever somebody has a risk of high heart attack, their BP may be elevated. So it's very natural to now the model to think that blood pressure has a high attribution on the risk for a heart attack, right? Very natural, because that's what maybe the model may be seeing in your data. But everybody practicing in medicine would know that blood pressure is not the cause for a heart attack, right? There is some other inherent cause which is causing increase in blood pressure as well as the risk for a heart attack, which are known as confounders in causality. So how do you separate causal attribution from any other kind of an attribution is very important, right? So because for a patient to know that their increased blood pressure is the reason why they may have a higher risk for a heart attack is not very useful. They may be more interested in what is the inherent reason why my blood pressure is high. That's what makes it really actionable, right? So that's what one of the directions we have been looking at is to how do you separate causal attributions from correlational attributions? Right? So this causal attributions are what you can really act upon. So how do you isolate them from other kind of explanations is something that we have been working on. One of our earliest works, I'll talk about it briefly in the next few slides. We've also done some work on doing visual explanations, explaining the decisions of a convolutional neural network on images. We have been looking at trying to get rationales for predictions. How do you get human understandable rationales for predictions? And we've also been looking at the intersection of explainability and what is known as adversarial robustness over the last few years. I'll briefly talk about each of these in the next few slides. One of our earliest works in this space was called GradCam++, which was published in 2018. And the notion of this is to, given an image, if a convolutional neural network makes a certain prediction on the image, can we find out which part of the image the model was looking at while making the prediction? Why is this important? If I have an image of a cat on say grass, if the model was looking at the cat to call it a cat, I trust the model more, as against the model was looking at a tree and calling it a cat, right? So maybe it's possible that all your images in a data set had a cat always with the tree. Now the model thinks that whenever there's a tree, the image should belong to that of a cat. Okay, this is a problem. Right? So this is really a problem. Right now, I could imagine that in, say, COVID chest X-ray images, it's possible that a lot of the chest X-ray images coming from a certain hospital may be COVID positive because they were designated as COVID positive hospitals. Now, if let's say there was some small marker on a chest X-ray that had the hospital's logo or name, now the model is going to think that whenever that name comes, the person has to be COVID positive, right? These kind of correlations the model may end up capturing from a given image, but that's not useful, right? So trying to know what the model was looking at while making a prediction becomes very useful to know in practice. So this work of ours has received a lot of attention, has been used practically around the world, has been used to explain COVID-19 diagnosis in chest X-rays, is being used to find defective cells in solar arrays, is used to explain cancer prediction on gene expression data, pathogens in tomograms, leaf counting, genus classification, so on and so forth. We've also been looking at trying to come up with human understandable rationale in decision making. For example, I mean, here is just one example application where we showed this. This task is known as visual question answering, where given an image and given a question on that image, the model or the neural network model has to give an answer to that question. So you see here that the image is this particular one. It's a scene from a movie. And there's a particular box here. And the question to the model is, why is person one covering his face? Okay, this is the question asked to the to the model about this particular image. And the answer that's generated by our model after training is he's trying to avoid getting burned. Okay, now we want to know a bit more. Now the human asks the model, can you give a reason why you're giving this answer? Then the model generates the reason that says there's a fire right in front of him. Okay. Both these are completely answers and rationales that were generated by a model. Okay, completely generated. Let me show you one more example. Here is an image. The question to the model is, what is person 8 doing right now? The answer that our model gives is person 8 is giving a speech. And if you ask, why do you say so? Why do you think the person 8 is giving a speech? The rationale is person 8 is standing in front of a microphone. Makes sense, right? So these are all answers and rationale completely generated by our approach in this particular work. This work is also publicly available on arXiv, and the code is also publicly available if you'd like to take a look. We've also been looking at the intersection of what is known as robustness and explainability. So adversarial perturbations is something very common in deep learning today, where you could change an image by a small few pixels and the decision of a model completely changes if you just change a couple of pixels. Right? If you take an image of a cat and change 2 pixels, the model suddenly starts predicting it as an ostrich with 99% confidence. This is known as adversarial perturbations, and one could use this in security applications to hack biometric systems and so on and so forth. Right? So protecting ourselves against such perturbations is known as adversarial robustness. And we've been looking at the intersection of explainability and robustness, because if you could explain every decision in a sane manner, there's no way that a cat image with 2 pixels change can be explained as an ostrich succinctly, right? So explanations and these kinds of adversarial perturbations on an image are closely related, and that's something that we've been looking at over the last few years. As I already mentioned, we've also been looking at the connection of causality in explainability, because it's not just about explanations, it's about what causal relationships lie between inputs and outputs that may be more important in practice, especially where you need your outcome to be actionable. Okay, so we've also recently been looking at developing data sets to study these kinds of problems, because unless you have data sets to study these problems, it's not possible to study them in practice. I'm quite sure all of you are aware that machine learning and deep learning are data centric. If you don't have the proper data sets, you cannot study the problem. So we've been looking at problems where we know the causal relationships between data, so that way whatever explanations we come up with can be validated and verified by knowing the ground truth. Just a couple of slides before I close in terms of open problems and challenges. The multiple interesting open problems and challenges in this space. Right? One of the fundamental things is, especially when we deal with images, I talked about multiple approaches where we say that by explainability, what we want is to know what the model was looking at while making a particular prediction. Typically, we call these saliency maps to understand which part of the model was, which part of the image was considered salient while making a particular decision. And more recently, there have been studies that say that these kinds of explanations may not really be useful in practice. Okay, so that again goes back to my first point that says that explainability is inherently a subtle concept. Right? It can vary based on who is at the other end of the line. So how do you come up with generic explanations, or how do you adapt explanations to different users of a system is still an open problem and challenge at this point in time. There have also been recent studies that humans' preferences on explanations can change based on what kind of data is presented. If it is an image, humans may expect different kinds of explanations. If it's text data, humans may expect different kinds of explanations. If it's speech data, people may expect different kinds of explanations. So even this now becomes a challenge as to what kind of explanations should be given to humans at a given point in time based on what data and what application the setting is in. There's also an interesting example here to show that context actually matters. Here is an example of an image which was an obstacle detection task. And one of the state-of-the-art explainable methods showed that this was the obstacle in the image. Right? So you can see that the red region here, which is where the heat map gives a high value, is the actual obstacle in the image. It's quite simple for a human to look at and say that you need to look at the bigger picture. This is the real obstacle. But the model thought that the break in the track was the real obstacle in this particular scenario. Right? So this is where I was talking. One needs to understand what is the cause of a certain observation rather than the observation itself. The context and the entire, what are called as confounders in causality, they matter when you talk about explainability. Just one last slide. So a few other open challenges is there a universal formalization for explainability in machine learning becomes a fundamental question. As I said in the very beginning of this talk, there is an inherent trade-off between accuracy and interpretability. How do you balance that? How do you ensure that accuracy does not suffer when you add interpretability to a problem? Is interpretability always required? What class of problems do you need interpretability, and when do you not need interpretability? I think we need better understanding of that too. How do you evaluate these kinds of systems still remains an open problem. A lot of how things are evaluated these days are largely based on heuristics. And whenever you use post-hoc explainability methods, who owns the explanation? Right? So if Infosys had to give a reason to the German bank on what was the reason, what was the reason for making a particular decision on a customer, and that let's say there were two different teams in Infosys, one developed the machine learning model and one developed the explainability layer on top of the machine learning model, which went wrong? The explainability method or the machine learning model? Whom are you going to sue? Okay, as legal affairs come close to AI technologies, these kinds of questions are going to become very important. And finally, AI has always had a legacy of a fight between two streams, a connectionist form of AI and a symbolic form of AI. A symbolic form of AI is where you talk about logic, reasoning, so on and so forth. And I think explainability is a very nice setting for these two streams of AI to work together for logical explanations rather than use one of them to derive explanations in general. With that, I'll probably close. If any of you are more interested, there are some very nice more resources online. There's a tutorial called XAI tutorial, which is a series of tutorials, which is suffixed by the year in which it was offered, which offers a lot of resources on explainability in general. There's also a very nice book on interpretable ML, which is publicly available by Christopher Molnar. If you're interested, that's another space to look at if you find any of this interesting and would like to know more details. With that, I'll stop this talk and I'll be happy to take any questions. Thank you again for your patient listening.
Thank you, Professor Binit. It's a very beautiful talk and informative and engaging. I guess our audience will have a lot of questions. I do have, but I will keep my questions aside for the time being. So for audience, if you have question, you can raise hand. You use that option. And also I will read some questions from the chat box, which I can see. So I'll read for you, or if you are there, you can unmute yourself and answer the question directly to the speaker. So maybe first I will start with Dr. Allah Sribani. Are you there? Allah Sribani? Not there. Looks like okay, maybe we'll come to her question later on because it's something to do with some software details. So there is one question from Uday asking, self-driving cars uses AI and ML for auto driving. Is this boon or curse?
Okay, so I think any technology has two sides. I think everybody in this audience, I'm quite sure, knows it. I think everybody talks about dynamite, which is probably one of the earliest earliest technologies which had two sides to it. So I think every technology has two sides. I think obviously we are working on self-driving cars because there is convenience and other use benefits of such a technology. And any such a technology also comes with its own risks. I think we all know that there have been accidents in the past. So I think one of the largest use cases for explainability is actually in autonomous navigation. If a particular, for example, one of the simplest cases where machine learning is used in an autonomous navigation vehicle is to predict the steering angle, right? Because at every point in time, the steering angle has to be predicted by a machine learning model based on the perception of the scene around using a lidar or a set of cameras or whatever are the sensors that are on the camera on the vehicle. Based on that, a model has to predict what should be the steering angle predictor. So if now you suddenly get a prediction as to take a left turn, maybe somebody should know why a left turn should be taken, especially if it's something anomalous, right? If it's a sudden left turn, right? So then maybe there should be an explanation of why it's done. Maybe it's because somebody is standing, some obstacle is in the front, so on and so forth. So explainability is very important in autonomous navigation. Many people studying this at this point in time. But in general, I think it's another technology which has its own benefits. I think there are many benefits that can emerge over the years, but it has to be very carefully implemented. And that's the reason why these topics are very important, right? Responsible AI, understanding the ethics of AI, understanding the legal aspects of AI. I think, in fact, this notion of explainability today, a lot of these discussions are happening in legal experts, like many legal experts in India today. I mean, I can give you one example. You can look up this website of a policy institute called Vidhi Policy Institute. I think Vidhi Legal Policy Institute or something like that, based in Delhi. They do a lot of work at the intersection of law and AI, right? So very important, especially in these kinds of applications, right? If an accident happens and somebody really suffers, it's very important to know whom to attribute it to, right? It's important to know, it's not about, obviously any damage is damage, it's very, very serious, but we also need to know how to regulate these things in practice so that manufacturers of such vehicles also take precautions and follow these regulations in practice, right? So those are important things to keep in mind. Obviously, it has its own benefits too. I'm quite sure I don't need to enumerate that.
Okay, thank you. Shibam Verma, are you there? Shibam Verma? You can unmute and ask the question if you are there. Okay, if not, then I will read this a bit longer. So he's asking, how does one define a kernel for a CNN layer for, let's say, edge detection? Is there a way to find such a matrix, or is it a trial and error to get a kernel that does a particular thing to our input image?
Sure. Okay, so I know it's a pretty technical question, but let me go into it. So generally it's understood, it's well understood today that the early layers of a convolutional neural network actually capture low-level characteristics, right? So in fact, one of the successes of convolutional neural networks is that they seem to be capturing data representations similar to how humans operate, right? So if you considered visual processing as a pathway, so that way your photons fall on your eyes and then your eyes go all the way, this information is carried all the way to your visual cortex through a visual processing pathway. So you start with your rods and cones, which recognize small textures like edges and orientation, so on and so forth. That now builds into higher abstractions in your visual processing pathway, like noses and ears and so on and so forth. And finally, at the back end of your visual cortex is where you cognize and recognize objects in front of you, even in terms of a simple visual processing pathway. It happens that convolutional neural networks seem to have a similar approach, right? So I think it's not intended to mimic, but I think they seem to have a similar thing, that the early layers of a convolutional neural network capture artifacts like edges and textures and orientations, and the later layers of the neural network capture higher level abstractions of whatever application you're looking at. So I think even without doing anything, today it's understood that the early layers of neural networks capture edges. Having said that, I think there are also methods today that can force the early layers kernels to learn a certain kind of artifact, like edges, for instance, right? So there are, if you look up edge priors in CNNs and things like that, you'll find papers that talk about how do you enforce early kernels in the CNN to form to do a certain task that you expect it to do. The last thing you can also think of is we already know kernels for edge detectors, right? Image processing for many years, like if any, since I'm assuming since you asked the question, you probably know Sobel edge detector or many other edge detectors have been proposed over the years for image processing tasks, right? So now you can always have the same kernel in your CNN and not update those weights. Then they'll continue to detect edges even otherwise. Whether you choose to update the kernel weights or not is in your hands when you train a neural network. If you now force a kernel to detect edges, you just incorporate a Sobel edge detector or something like that, and just don't update your weights over the training of a neural network, you get a kernel that detects edges that's inside your convolutional neural network. You can also do that if that's what you want to achieve out of a CNN.
Okay, next question, Yashwini Kaur. You have also raised hand, so you unmute yourself and ask the question. Yashwini.
Good morning, sir. Am I audible?
Yeah, you are audible. Please go ahead with
Okay,
your question.
yes. So, sir, just I have a query. Please suggest something on implementation. Is it like, means whenever we are training the network, is it like we have to feed something extra so that explanation can be obtained in the output?
Sure.
What do you suggest?
Sure. So as I mentioned, I think existing methods are of two kinds, post hoc and anti hoc. Post hoc methods are where you don't feed anything extra. You just learn the normal way, and the explanation is something that's derived from a trained model after training, right? So this is the more common approach. If you ask me, 90% of the methods or 95% of the methods today are based on such approaches. There are other approaches which are a bit more recent where people are trying to see if while training itself, you can add what is known as a regularizer or something like that to ensure, for example, let's say that you knew from domain knowledge that a certain input had a monotonic relationship with a certain output. How do you ensure that monotonicity is maintained by a neural network? Can be done by adding what is called as a regularizer in your loss term. If you want to do that, yes, you may have to change the loss term slightly while training the neural network in terms of implementation. But for most of the methods that I talked about, there are already public libraries. Please look up this library called Captum by Facebook, which already implements all of these explainability methods, especially if you're using deep learning. There are all of these methods that are already implemented, and you can straight away use them from these toolboxes.
Okay, sir. Thank you. Thank you.
Sure.
Okay, Sayok Ash, are you there? Let me check. Sayok, can you unmute yourself?
Yes, sir.
Yeah, you can ask your question directly.
As explainability is highly subjective and differ from person to person, how can you be sure that explanation is not biased?
No, as I mentioned in the talk itself, I think that's one of the challenges for us, right? It's not easy. I don't think there's a clear answer for that question. The only answer we can give at this time is that for a given application, you have to decide based on who are the stakeholders, who are the end users of that application, as to what explanation may be meaningful. So based on what the user thinks is meaningful, we have to see how can it be presented or what can you extract from the model to present to the user based on what the user thinks is useful. So it has to be, I think it's very difficult to answer that question across applications as a generic answer. It has to be application driven. So if someone is using application aerospace, they have to see what a pilot may need. I mean, let's assume now a machine learning model is used. I'm not sure if you know, but many airline companies are today trying to go for a single pilot model for long haul flights, right? So today, you know that most flights use 3 pilots or some 2 or 3 pilots for long haul flights. So then if a machine learning model says now drop 1,000 feet, a pilot may want to know, why are you telling me this? Is there an aircraft in front of me, to the left of me, to the right of me? Maybe that's useful in making other decisions, right? So So it depends on what a user may want in a particular setting and accordingly give explanation. So I think because it's subjective, one has to understand the application and then decide what could be the most useful explanation in that context.
Thank you, sir.
Okay. Mathia Yazhan, can you ask your question? Unmute yourself. Okay, let me read out. So she's asking maybe how MI or L is useful or influenced in the field of energy, especially in renewable energy field.
Sure. I think plenty of use cases. I think renewable energy by itself is a very, very vast field. I think it can go from solar to oil and natural gas. And I think the space is extremely vast. I mean, a couple of examples that I know is, for example, solar farms, right? So many of the solar farms these days use machine learning for multiple steps, right? One simple use case across all of these kinds of large setups is predictive or preventive maintenance. Right? So because if you have a solar farm, to know when a solar panel may fail, or to automatically find out which panel has failed in a farm is not trivial. Right? So people today actually fly drones to get images of a solar farm and then try to find out where a particular failure may have occurred. Machine learning is extremely useful in this kind of a scenario. I mean, solar farm is just one example of renewable energy. There are also things like, let's say you have an oil industry or a natural gas industry or things of those kinds. Refineries these days are mandated that there are certain chemicals that have to be burnt before they are released into the air, right? So this is mandated. I think the fines for these companies are huge, like of the order of hundreds of millions, if they don't burn such things before they release it into the air. So these days, people use machine learning to find out whether from a refinery the smoke is coming out as a flare or not, right? Just to simple things, right? Just to have, there is actually a person who's stationed on a surveillance camera continuously to check whether a refinery is releasing a flare or not, just to ensure that they conform with the regulations. Now, these kind of things can happily be replaced by machine learning, right? So I think I just talked about a couple of examples. I don't work in that space, and I'm sure there are many more. But I think it's plenty of use cases. But once again, I think it's important to keep in mind that it's not that machine learning is the only solution to all problems, right? So that also should be kept in mind. I think it depends. I think certain problems can be solved by machine learning, and certain problems perhaps don't even need machine learning. I think it's also important to make that distinction and use it where it's useful. I think it's also, and the best person to answer that question will be a domain expert. Right? So they would be the best people to answer that. I think, which is perhaps the reason why I think every field needs machine learning experts today. Whether you're in the renewable energy field, whether you're in the material science field, whether you're in the semiconductor industry, I think people need experts who understand both domains, understand machine learning, understand the industry as well, so that they know what can be used where. So it becomes very important.
Okay, Pranab Srikar. Pranab, can you unmute yourself?
Yes, sir. Can you hear me?
Yes, I can hear you. Go ahead.
Yes, sir. Yes, sir. Sir, I have a question which is not based on the subject right now. Can I ask?
Okay, let's see. You ask.
Sir, I have learned machine learning 3 months back, sir. And I'll make computer vision software for organizations, and I have my own company, sir. Actually, my age is just 13 now. What is the next step can I take?
Okay, I think you're already doing well for 13. So, but I mean, very incidentally, I in fact have an intern who's 13 years old. His name is Siddharth Pili. You can look him up online. So he's been interning with us for a year. In fact, he's also similar. So I think, I mean, you're already doing the right things. I think it's at your age, I would just say you should follow your passion, right? So it's I understand that if you have your own software company, you probably need to learn what you need to solve those problems. It's I think there are two ways to go, right? One is pick up a field and be the best you can be there, so you can then put that to use. The other thing is have a use case and pull in technologies that you need to solve a use case, right? If you have a company, I assume that you have a use case. So then it's important to see what technologies you need to solve a use case and accordingly pick them up as you go. Many of these, luckily, most of these domains, the subject matter is already available online. So you probably just need to learn what is it that you need to solve the problem that your company is trying to address. But once again, yeah, congratulations for your achievement. I think at age 30, that's a commendable achievement.
Yes, thank you, sir. Thank you, sir.
Okay, Uday Kondeti.
Yes, sir.
Yeah, you can ask. Go ahead.
Good morning, sir.
Good morning.
Yeah, we can hear you. Go ahead with your question. Quick.
Sir, can open source explanations on machine learning can break the biased genre, sir, as we can collect more data points to make program accurate?
What do you mean by open source explanations?
As we have open source softwares like Linux, where all can contribute their work. Can they contribute to the machine learning?
Sure. I mean, most of machine learning software today is already open source, right? So I think TensorFlow, PyTorch, which are all common frameworks that are used for deep learning, are already open source, right? So they are contributed by different organizations. Many organizations build on top of their stack. So they're already open source, and many of them, there are PyTorch library for explainability, which are all already open source, right? So that's already happening at this point in time. But remember, explainability can need expertise, right? So in fact, one of the ways to get the ground truth for explanations is to ask people. In that sense, if you're talking about open source, remember, for all domains, everybody may not be able to give explanations. Right? So for example, if you're trying to solve a problem in bioinformatics, only a certain set of people can be able to explain decisions there. You need experts, right? So not everybody can explain decisions in those kinds of scenarios. But if you're speaking from a pure software perspective, most of these algorithms and so on are already in open source libraries.
Thank you, sir.
Yeah, okay. One more question, maybe a couple of last. So one question I picked up seems fine, that it says that as shown in earlier slides in the plot between interpretability and accuracy, what can be done to increase the interpretability of highly accurate algorithms, say neural network?
So, which is exactly what the second part of my talk was talking about, right? Which is how do you bring interpretability into neural networks, right? So as I said, there are probably two ways of going about it. One is after you train the neural network, you explain, or the other way of going about it is use what are known as regularizers, which is something that you add while training a neural network to make it more explainable, right? So both of these are what are used to actually make highly accurate models like neural networks more interpretable.
Okay, Nirmal Deep. Nirmal Deep.
Yes, sir.
Yeah, please go ahead quickly. We have 2 minutes only.
So may I know what about the online course of BSc Programming and Data Science and Programming in January?
Okay, I am actually not from IIT Madras. I'm from IIT Hyderabad. So I'm not aware of that. I'm quite sure. I'm aware of the course from IIT Madras, but I'm not aware of their timelines. I think you may have to email your administration to check on that.
Is it better to have a BSc degree in data science and programming, sir?
I think it depends on your background and your interests. Yeah, definitely data science and programming is relevant to all disciplines today. It depends on what.
I'm from CSC background, sir.
So in most CSE, depending on where you're studying CSE, in most cases, you would anyway be doing machine learning and programming as part of your coursework. So to a large extent, you may already be doing this, but definitely such a course is going to add value, right? So definitely how much value may depend on what you already know, right? So that part is maybe difficult for me to say without looking at the other aspects of your learning.
Thank you, sir.
Maybe we are already learning out. I also had a couple of questions, but maybe I just want to ask one from Neeraj Sharma has one more. Okay, let me take that. So how can we design or modify a CNN architecture in the case of transfer learning? What kind of approach we have to follow? Is bio-inspired can be a good option?
Okay, these are actually two different questions. I think for transfer learning, there are already enough methods. I think it's transfer learning with CNN is a very, very well studied topic for the last several years, in fact. So it's very common to, depending on how close your target domain is with respect to your source domain, based on that, you choose to take a CNN model and decide which layers you want to fine tune, the weights of which layers you want to fine tune, and then adapt it to a target domain. So that's what transfer learning is. And there's plenty of discussion, blogs, papers in this over the last few years. By bio-inspired, I'm not sure what you mean. It's a very, very vast topic, right? So I mean, you could say that neural networks themselves are bio-inspired in a way. So it can start right there. Or if you're talking about things like genetic algorithms or ant colony optimization, swarm optimization, things of those kinds, that's a different topic altogether. So I think bio-inspired is a very, very vast topic. So it's very difficult to probably answer that in one line. I mean, it is a good option. Everything has a purpose, but depends on applications and the limitations that it may have in an application.
Okay, maybe I just want to ask one question. I have several, but we discussed about several models like LIME and LRP, all those models. I just want to know in the LIME where you was discussing two images and you had a weighted distribution, right? Which part of this image gave you that information correctly, something like that. So how you drew this plot and how to infer, rather how to get those blurred images, right? You cropped certain parts of the image.
Sure.
And so is this after training, and how this whole thing works? Can you briefly mention that?
Yeah, absolutely. Of course, I think the paper has more details, but in this particular case, what they do is these are random perturbations. So you just take an image and randomly choose to occlude different parts of the image, just randomly. That's all. And now try to propagate the same image to the neural network and see what is the probability of a tree frog. Has it increased or decreased? Right. So you have the original image. The original image had 0.54 probability of a tree frog when you propagate it through the neural network. Now you randomly perturb the image. When I say randomly perturb the image, you can do a couple of things. You can first segment the image and randomly on and off segments in the image. Right. So that's also possible. Right? So that's also something that's possible here. So then you propagate that through the neural network and now see what is the probability. So now you have a new set of images, which are perturbed images, and their corresponding probabilities. Now, what you build is a regression model between this new x's and the y's, which are the probabilities. Now, this regression model will have a weight for each feature. Now, that tells you which feature had the highest attribution towards the output. And based on that, you can tell which part of the image is the most responsible for a certain outcome. So this is something that you have to build a regression model for every data point. So it's in that sense can be time taking. So this is a post hoc model, which means you do it after you train a model. So as the name states, LIME stands for local interpretable model agnostic explanation.
Yeah.
So which means your base model need not have been even neural networks. It could have been SVMs. It could have been decision trees. It could have been any model. Any model, it gives you a probability for a certain input. Now perturb the input, see how the outputs change. Now build a regression on these perturbed inputs and the corresponding outputs. Those weights in the regression model can tell you which input attribute had the highest attribution outcome. And you can do this for any data. I showed the example with an image. You can do it with tabular data. You can do it with natural language. You can remove and keep some text, words in a text document. You can do with any of those. They in fact show results with multiple kinds of data types in their work. And the code is also publicly available. In fact,
so this LIME and this LRP, the Layerwise. So which one is more robust, or is it depends on the problem?
I think depends on the problem. I think it depends on the problem. So, I mean, if you ask me, I want to try a couple, which ones should I try? I would recommend LIME and probably integrated gradient. Integrated gradient and SmoothGrad are a bit more popular today. In fact, there are variants of integrated gradient also, but I won't get into it. But probably LIME integrated gradient. LRP is also popular. It has a nice code base which people use. But LIME integrated gradient are perhaps among the most popular. Shapley values are also something that can be tried. Right? But these
so all these methods, these GitHub pages are available, right?
Yes, the code is publicly available.
Okay.
As I mentioned, there's also a library called Captum that's made public by Facebook, which has many of these methods pre-implemented.
Oh, okay. Okay. Okay, I think our next speaker is already waiting for 5 minutes.
Sure, yeah.
Thank you so much, actually. Really, it's a very good talk, and we have gathered a lot of information. And I do have a lot more. Maybe we can have chat separately over email. I will contact you later on. And also, as I said in the beginning, we really want you also maybe on campus someday, and so that we have greater time to discuss and exchange ideas. With that, thank you so much, Professor Vinit. Yeah, thank you so much.
Thank you. Thank you very much again. Thank you.
Okay, it's time to go to our next talk. So our next presentation is by Dr. Girish Verma from IIIT Hyderabad. And he's a faculty member at the Center for Security Theory and Algorithm Research, and of course the Machine Learning Lab at IIIT Hyderabad. His research interests broadly in theoretical and applied computer science problems. He did PhD from TI from Mumbai on computational complexity theory, and then continues to work on complexity theory, combinatorics, game theory, and many more interesting topics in the field of computer science. He has published several articles in peer-reviewed journals and premier conferences. So we are very happy, Dr. Girish, that you have accepted our invitation. We are really looking forward to your talk. And the title of the talk is Deep Generative Methods and Applications. Over to you, Dr. Girish.
Can you hear me?
Yes, we can hear you.
Yeah. So thank you, Dr. Amit, and thank you for inviting me for this symposium. It's very interesting to meet so many people, like 200 people. I wish it was a physical meeting, and it would have been much more interesting. So, so let me share my screen.
Yeah, we can see. Yeah, we can see. Yeah.
So, so my talk is about generative models and applications. So I am a faculty at IIIT Hyderabad, as Amit said. So, my experience with using machine learning physics is not that much. But I do collaborate with faculty in the science department. So I talk to science students also working on machine learning problems. And very frequently, I see that they need to use generative model techniques in their problems. Yeah? So hopefully, I will be able to give you some of the basic techniques. Describe them in some detail, and also give you one example work on machine learning in physics, generative model application in physics. In which I was part of also. Okay, so let's get started. So before I start, I see that there is a wide variety of people. 200 people, meaning there are people who understands different parts of machine learning. So if you have a question, please stop me. I would like the talk to be as much as interactive as possible. Don't hesitate to stop me. Okay, at any point of time. Okay. Okay. Let's get started. Sorry, just a second. Yeah. So that's a summary of my talk. Yeah. So I'll be starting with describing what generative modeling is. Yeah. And we will see some examples, very mundane examples from computer vision, speech. And I will describe some of the most popularly used techniques. Yeah, there are various techniques in generative modeling, but three most popular techniques that is very commonly used, I will be describing. And finally, I will describe an application to materials generation. Okay, so you want to generate materials with specific properties, physical properties. Yeah. So this is the plan of the talk. Yeah. So let's get started with the basic problem which you are all familiar with, right? So you have done your experiments. Yeah, you had some input parameters. You had some output observations from the experiment. So you have some points, and you want to fit a model, right? And you can play around with different functions. You typically fit in MATLAB or Python, and you basically fit your model. Yeah. And machine learning to a large extent is also this. What is called supervised machine learning is basically this only. You are just fitting more complicated functions. Okay. So what is different in a generation problem? In a generation problem, the data is much more complex. Yeah? So your y doesn't directly depend upon x. So your y might depend upon other factors as well, not just x. Maybe there is some noise, yeah, added to x, and then only your observation is obtained. Yeah? Maybe there is some other latent factors influencing the output of your experiment. In which case, the dependence between x and y is much more complex. Yeah. So maybe the output of your experiments you plotted like this. There was a lot of points, and as you see, the y is not a deterministic function of x. There is no nice line or any simple curve you can fit on this data. Yeah. So what is a reasonable thing to do? So a reasonable thing to do is instead of predicting, finding a function which fits all these points, what we will do is for every x, for every input you find a distribution over y's. Yeah. So you would like to find the distribution over y's given a x. Yeah. So that is the probability of y given x is what you would like to find out. Yeah. So here you are finding out the single value y, and here you are actually finding a distribution over values y, and that is the basic difference. Yeah. And for example, in this particular case, what is a good thing to do in this particular case? Anybody wants to think of what is a right thing to do in this case? So one approach is for every x, you will output, let's say a mean value mu and a variance sigma. For every x will be mapped to a mean value mu and a variance sigma, and basically you will be sampling y from the normal distribution of mu sigma. Yeah. And the mean naturally is given by this straight line, and the variance is, let's say, for this particular x, it will be this spread. Yeah. So it might not look like a actual Gaussian in this particular case, but this is one approach to doing it. Yeah. So so as we said earlier, we are not predicting a single y. Yeah, we are actually predicting the distribution. The output of a generation problem is a distribution over outputs. Yeah. And so one thing that you can do, so when you see this data, so there's a very natural thing that people will do. Yeah. So as you see, it looks like a Gaussian in 2 dimensions. It looks like a Gaussian with center here and points sampled around that. Yeah. So if you have this particular data, a natural thing to do is you kind of compute what is called the principal components, which will be these 2 directions, and it's basically you can see that it's actually a Gaussian, with these 2. This is the major axis, this is the another minor axis, and the standard deviation along this axis you can compute by using the singular value decomposition. Okay, so these are very standard techniques that you do in data analysis. Yeah. And so for every x, you can in fact you can find the joint distribution of x and y itself in this particular case. Yeah. The joint distribution of x and y itself is a 2-dimensional Gaussian. Yeah. the 2D Gaussian, and the variance along the different axes can be found by the singular value decomposition. Okay. So yeah, this is a simple example, but in real world, your input and output is not going to be scalar values. It's going to be a very complex distribution, yeah? And you cannot find out the distribution exactly. Okay, and that's what we are going to talk about. So let's see. So yeah, so let's look at a more complicated problem. So you have some data set of images. I mean, I work mostly in computer vision, so my examples are in the beginning will be mostly from the computer vision part of things. So there are a lot of images, and we would like to generate more images like that. Let's say, okay, for your training, for you want to build a classifier, and some of the classes didn't have enough examples. Yeah? So you want to generate more images of that particular class. Yeah? And let's say, so what do you do? Yeah? So you can build a generative model, yeah, which fits this distribution. And this is slightly different from what we said previously. Yeah. And previously, you are given a yi and then you are predicting this distribution. In this case, there is no xi even, there's no input. Yeah? So you are just directly predicting, just want to sample an image which looks like the dataset image. So we are just sampling images, and yeah. So so this kind of generation is called unconditional generation. So you are just sampling images from a probability distribution. So yeah, so we want to learn a probability distribution which is similar to P data, which is unknown. We don't know what it is, but we want to use a machine learning model to learn this complex distribution of images. Yeah. So yeah, so this is the unconditional generation problem. Yeah, and this kind of generation problem is one of the main use cases of this is unsupervised learning. Yeah. So if you have, heard about machine learning, one of the main problems in machine learning is in many areas there is not enough data. Yeah, you might be running some very slow quantum mechanical calculation. Then you might be only able to run 100 experiments or so. Yeah, and when you have only 100 experiments, 100 xy values, it's very difficult to train a big deep learning model there. Yeah? So you want, some unsupervised training where typically the number of inputs is very large. You might be able to find the correct label y only for a very small subset of inputs. Yeah. So your input set is very, very large. Yeah. And your labeled input is very, very small. Because okay, there is only limited computing power you have, so there's limited number of experiments you can do in the lab, because of which is required to get these labels. So the number of labeled examples is very, very small. So this unsupervised learning allows you to train the model, a large part of the model, in this big input space. Yeah? And maybe little bit part of the model we will train on the labeled examples. Yeah, we will come to that in a minute. So so this generative models is also a very strong way of doing unsupervised learning. So there are various types of generative models. Yeah. In the earlier example, for every y, for every x, we could actually find the exact distribution of the y's. Maybe it's like a Gaussian distribution or something like that. And we could also find the joint distribution by just computing the SVD. But in this particular case, the distribution is not going to be a simple distribution. So the input itself is so much complex. Yeah. What is a image? Image is actually 3 matrices. Yeah. There is a matrix corresponding to the red channel. There is a matrix corresponding to the blue channel. There is a matrix corresponding to the green channel. So here the input itself is such complex. It's 3 matrices together is one input. And it's not going to be a simple distribution. You will not be able to simply model it by a Gaussian or anything like that. So in that case, we wouldn't like to write the formula of the, you wouldn't be able to write the formula of the distribution, but rather you would just be able to sample from the distribution. And that itself will be useful in many tasks. You'll see some examples later. Okay, so yeah, so you might ask what is new in all this. Yeah, so this people have been doing, even in science, scientists have been doing this for 70, 80 years. Yeah, so people have been doing function fitting, people have been doing probabilistic algorithms. Physics community invented what is called the Monte Carlo algorithms, which does generative modeling exactly. And this have been around for 60, 70 years. Yeah, so I mean, in some sense, there is nothing new. It's strange, right? I mean, physics community were working on it long time back. Now there's a big area called machine learning, and now we have a symposium called machine learning for physics. Yeah, so it actually originated in physics, many of these techniques. Yeah, but the new thing is, so ML became its own field because it has all these applications coming up, yeah, in computer vision and other areas. It also came up with new algorithms, yeah, and function classes and everything. Yeah. So the new techniques that we give today in the lecture is mainly originated in the machine learning community, yeah, independent of the physics literature, and it started getting adopted in by physics people also. Yeah. So I'm sure your faculty there would be much more knowledgeable about some of these things. So yeah, let me just give an introduction. Okay, so let's see some examples of generative modeling in computer vision. Yeah? So so this is a very nice example. So you have some low resolution images. You got some low resolution images. Can you convert the low resolution image to a very high resolution image? Yeah. Usual intuition says that no, I mean, it's a lossy transformation. When you go from a high resolution to a low resolution, it's you are losing a lot of information. How are you going to convert a low resolution image to a high resolution image? Yeah, but the thing is, for example, in this case, they're only looking at faces. The type of images you can have as faces is actually very, very less. So actually, the low resolution image has most of the information about the face. And if you can learn the right mapping between low resolution to high resolution, yeah, using and you can generate training data for this. Yeah, you can basically invert that transformation. And yeah, so you're kind of given the low resolution image, you are predicting the high resolution image. So this is a sample from the high resolution. Yeah? So it will give you a probability distribution, and you can sample from that distribution. And this is an example of a sample from the distribution. Same thing here. So you have some image, and there are some parts are eaten by an ant or something like that. And can you recover the image? Yeah? And it has been demonstrated that to a good extent it can. Yeah. So you might have seen a lot of there are documentaries of World War II, which was actually shot in black and white during that time. Yeah, which is converted to color. Yeah, you can see in your Netflix and everything this kind of documentaries. And how is that working? So again, you are basically given the grayscale image. Yeah, what is you are outputting a distribution over the color images, and you are sampling from it. And that's what is happening. And the techniques we are going to cover are the basic building blocks, yeah, used for that kind of problems. Okay. So yeah, this is another interesting example. Yeah, so there's a horse image. Yeah, you want to generate a zebra image of that, conditioned on that horse image, and yeah, it kind of gives what is intuitively it should be the output. So yeah, so this is another interesting example. So you can have a rough sketch like this. Yeah, you can just have a very childish sketch, and that childish sketch can be converted to a realistic image, yeah, using this generative model. So you'll be conditioning. So this will be your y, and this is your generated x. So you're kind of getting p of x given y. Sorry. Yeah. So you are given this y, you are generating the x. Okay. Yeah. So there are a lot more examples. Yeah. So let me give few more examples from language. Yeah, which is getting very popular. So I mean, this is, you already know, you can do language translation. Yeah, and given a particular sentence in one language, there could be multiple, I mean, sentences in the output language. Yeah? And you are typically sampling from the output using a generative model. So it's a conditional generative model that at work. So yeah, this is another interesting example. So here you type in some text. You go to this website, you type in some particular text, it will write a sentence, full paragraph, yeah, which can come as a suffix to that sentence. Yeah. So this is the sentence you have written, and it basically filled in all this. Yeah. So this was just trained on all the Wikipedia data or something like that. And the generative model could generate the rest of the text. Yeah, it was reasonably looking. So finally, actually, this was an animated GIF. I don't know why it is showing you. So this is actually what is called the GitHub Copilot. You can write a function and you can just comment what that function is supposed to be. It will write the code of the function. Yeah. So, and sometimes actually it gives valid code. Yeah, exactly what you comment here, it will write the code for that. Yeah. So it's, if you're a lazy programmer, it's yeah, there is some still hope for you. Yeah. So yeah, these are some examples of yeah, generative models. So generative models is a vast topic. Okay, it's been, yeah, there are a lot of I mean, there is a lot of inspirations from the physics community actually for the generative models, and yeah, but it became its own community. The machine learning became its own thing, and yeah, there are some new techniques that was, a lot of new techniques were generated. So in our first example, we could actually give the probability distribution itself as a Gaussian density function. Yeah? But in the images example, we could only sample from the distributions. Yeah? So depending upon the situation, there are multiple types of generative models. Yeah? So today we'll be covering these three: GANs, variational autoencoders, and what is called normalizing flows. Yeah? So this particular one. Which comes here. Yeah. So yeah, we'll limit to this three topics, which is most commonly used, but there are various other models. Yeah. So there are things like Gaussian processes and all, which is also used in the physics community. But yeah, I'm not going into that in this talk. Yeah. So is there any questions?
So far, I don't see any.
Okay, so
yeah,
yeah.
yeah. Okay, there is one, maybe just, what does density mean here?
Density means a probability density. That's it. So if it's a continuous function, it's a continuous variable, it's called a probability density function. And for example, for the Gaussian random variable, for example, the first example we saw, we know the mean and the standard deviation. So we exactly know the probability density function, which will be 1 by root 2 pi e raised to minus the Gaussian formula, right? So in tractable density, we can write out the exact formula, yeah, for the probability distribution of y, the thing you are generating. But in these kind of methods, in implicit density and everything, you can only sample from that distribution. You can generate samples from the distribution. You cannot write down the formula for it. Is that okay? Okay. I hope it is fine. Yeah. Okay. So let's carry on. Yeah, so let's start with normalizing flows, which is it's easier to understand in some way, the normalizing flows. So yeah, so what is a normalizing flow? So a normalizing flow is it's a transformation which converts a simple probability distribution, yeah, to a more complex one by a sequence of transformations. Yeah. So, I mean, you might like the Gaussian density function, but you cannot expect the Gaussian density function to model images, for example. Typically, many of this distribution, complex distributions, have like multiple modes. Yeah, it will more look like that rather than a single mode. So typically, a complex distribution will have many modes of various heights and everything, and you cannot easily model it by a Gaussian density function. So is there a question? Please ask. Okay, I thought somebody raised the hands.
Yeah, somebody raised the hand and then lowered.
Okay.
Yeah, maybe. Yeah.
Yeah. Please feel free to stop me and ask. Okay. Yeah. Yeah. So you cannot expect a Gaussian density function to model any images. Yeah. Any complex distributions. Yeah. But maybe you can slowly transform a Gaussian by means of some transformation into a very complex distribution. Yeah, please go ahead and ask whoever raised the hand.
Ramesh Kumar? Yeah. Can you unmute and ask the question? Ramesh Kumar.
Okay, yeah, maybe that was yeah, some mistake. Okay, let's continue. Yeah. So yeah, this is the idea behind normalizing flows. Yeah. So let's see. I mean, a little more concretely what it is. So you have some images, yeah, and you would like to find the probability distribution of that images. Obviously, the input itself is very huge. Yeah, I mean RGB, there are 3 matrices, and you would like to model it by a Gaussian, where some transformation applied into a Gaussian. Yeah, so your Gaussian looks like this. Yeah, very white noise. Yeah, there is nothing like your grains in your TV. So there is hardly any information here. How do you model something like this by something like this? Yeah? So what you do is you think that there is a transformation F, yeah, which maps this to this. Suppose there is a transformation, and as always nowadays in machine learning, all transformations will be neural networks. So it might be a multi-layered neural network with many layers. So some of them will be a CNN or RNN or batch norm. All those layers might be there. So so F theta will be a neural network, yeah, which maps this image to this. And so if you have one probability here, yeah, and suppose you are applying a function on it and getting another x here. So how does the probability distribution changes? So there's a standard formula for it. If you remember linear algebra in engineering mathematics, yeah, you will see that the distribution is changed by exactly the determinant of the Jacobian. Yeah? So Jacobian is the matrix of partial derivatives, and if you take the determinant of the Jacobian, that tells you how much volume here, yeah, is transformed here. So the probability distribution function of x and c will be related by this particular formula. And yeah, so this formula is true. This determinant has to be non-zero. Yeah, and in particular, this works only if f is invertible. So in general, neural networks are not invertible. Yeah? So what will you do? How do you go about building such a F? Yeah. Anyway, but if F were invertible, yeah, then you could actually get the probability distribution of X and relate it to the probability distribution of Z. Yeah. So yeah. So suppose you have a way of constructing it, which I will come to in a couple of slides. So how do you learn this? Yeah? How do you learn this probability distribution? Yeah. So yeah, basically we want to learn f theta of x, which transforms this p of x into p of z, yeah, into x into z. Yeah, and the theta is your learnable parameters, yeah, which you typically learn using backpropagation interval. So we'll assume that this pz is Gaussian distribution. It doesn't need to be a Gaussian distribution. It is any distribution which is easily parameterizable. Yeah? It has a very nice closed form formula. It can be used. But yeah, Gaussian distribution is the most easiest distribution to work with. So typically your latent vector. So this set is called the latent vector. So, and this is called the latent, pz is called the latent distribution. Yeah, so if you hear latent vector or latent distribution, it is this set which is sampled according to the Gaussian. Yeah. Yeah. Again, if there is a question, please stop me. Yeah. Yeah. So yeah, f theta should be invertible for our probability that formula to work. F theta has to be invertible network. Now, yeah. So given all this, how do you learn the parameters of the normalizing flow? Yeah. So yeah, so since this formula works because f is invertible, yeah, we can find the probability of x. So you have, let's say, a lot of images. X1 is one image, x2 is another image, xn is, yeah, you have n images. So for each of these n images, I can find the probability. I can find the probability of xi, yeah, by using this Jacobian formula. Yeah. Once we have this, yeah, so we would like, so in your training data set, whatever images are there, you would like the probability of those images to be very high. Yeah. So what we should do is we should find the parameter theta, yeah, such that the probability of those images is very high. So the probability of those images is given by this formula. So so for some reason, yeah, machine learning people like to put a log everywhere. Okay, so this is called a likelihood. But when you say log likelihood, yeah, you put a log here. So you just take the log of this. If you take the log of this, this will turn into a summation. So this plus this, and yeah, you would like to maximize the likelihood of all the n examples. So that's why there is a summation of 1 to n. Yeah. So you have some images and you would like to maximize the probability of seeing the images in your data set. Yeah. So yeah, so we write down the probability of each of these images, take a log, which will give out this formula, sum up all these values for the n images and take the maximum, try to find the theta, which has the maximum value. And typically, you can do this by gradient descent and backpropagation. Yeah? So optimize this by backpropagation. Sorry, I think my pen is too thick. Yeah, anyway, yeah, so you can optimize this by backpropagation. So yeah, so that's how you learn a normalizing flow. But now there is this big question. I mean, how do you design a neural network that is invertible? Yeah, I mean, neural network is yeah, this activation function, and the activation function is easily invertible actually. But I mean, a single neuron or a linear layer is, or even a convolutional layer, is typically a matrix multiplication. It's a linear operation, and in general, this matrices might not be invertible. Yeah, so you need to ensure that all the linear operations that you're using in the neural networks are invertible. Okay. So yeah, how do you build a complex normalizing flow? So the way to build a normalizing flow is just the same techniques that you do in deep learning. By composing a lot of simple functions together, each of which are invertible. Yeah. So you compose a lot of invertible functions together, and together it forms a deep network, and that way a simple Gaussian can be converted into a very complicated distribution with lots of modes and everything. So so the interesting thing is when you have this function, when you want to compute the determinant of the Jacobian, it actually nicely separates out into a product of determinants of the individual thing. And when you want to compute log likelihood, that is a log of the probability of x. So by that formula, very nicely. So since the log of this will also become the summation. So log of this product of determinants will become summation of logs of the determinant. And each of these terms is very easy to compute, and you can do a gradient descent on this loss function. So so it's very easy to build normalizing flow. You can just maximize the likelihood of the data that you see from your experiments. So so we can create complex normalizing flows by composing functions. But what are the individual functions we can use? So there are two types of functions you can use. One is just have a linear transformation, and there is a standard formula for the inverse and the determinant if the matrix is invertible. So so it is very difficult to ensure invertibility when your transformation is a convolution. Okay, so there are actually a lot of research works on how to build a invertible convolutions. So I can give a reference, but it's an interesting topic of its own. So another approach is what is called coupling. So in coupling, you kind of split your input into two parts, and keep one part of the input as it is in the output. And in the other part, so this coupling transformation is typically addition. You typically add you can put an arbitrary neural network here, apply it on this XA and add it to XB. So your output would be XA concatenated with XB plus some arbitrary neural network applied on XA. So so G theta need not be invertible, but this function is still invertible. So you can easily derive that, because since you have XA in the output, the top part of the output, you can just and you know G theta. So G theta of XA you can compute and subtract it from the second part. So this will easily ensure that this is invertible. And the Jacobian and the determinant has a simple formula that you can work out. So these two are typically the two building blocks people use for building a normalizing flow. So this will be your F1, F2, F3. So this F1 might be a linear layer, F2 might be a coupling layer, F3 might be again a linear layer or a convolution, and so on. So so you can build a normalizing flow using these building blocks. So this is an example from a paper with my student Sandeep. So we were building normalizing flows, and so it gives a very interesting example. So so you have your latent vector set. By modifying the set values, actually, so this is an original image in the data set. So we could convert that image to an image without the glasses. So this is a completely fake image that you generated using a normalizing flow. Similarly, hair color you could modify. We could modify the facial expressions. And you could even tune the age parameter. So this is the original image in the data set. We could we could find a latent vector and we could tune that, latent vector such that to get a younger picture of the same person or an older picture of the same person. Yeah? So these are very, very powerful techniques, which find natural applications in many fields, including in physics. So I can share links to these. So any questions? Okay. So I think we are short on time. So let me quickly cover the other topics. Yeah. So the next topic is variational autoencoders. So to describe variational autoencoders, I need to first describe what an autoencoder is. Yeah. So autoencoder is again an unsupervised approach. All these generative models are typically unsupervised, and so it allows you to learn a low-dimensional feature, from unlabeled training data. So you're already familiar with how to get low-dimensional features, for a complex data set. Typically, you can apply your PCA, and project it down to your PCA subspace. That is one way to get it, but that is a linear dimensionality reduction technique. You apply a matrix and reduce the dimension. And autoencoders is a neural network way, a deep learning way of reducing the dimension of your input data. You don't want a high dimensional data because it's very difficult to train networks using high dimensional data. So we want to reduce the dimension of the data in an unsupervised way without any labels. Okay, that's the plan. So how do you do it? So you typically have a neural network called the encoder. So it will have some parameters E theta, and you have another neural network called the decoder, which has its own parameters D phi. And basically Z is essentially equal to E theta of X. And this D phi of D phi of Z is basically X hat. So X hat is what comes at the output. But we would want this X hat to be equal to X. So to train this deep learning network, we'll just take the mean squared error between X and X hat. Okay. So so for this you don't need any labels. You only need your input. This is the network which does nothing useful, which takes in something, gets some features set, and recovers back the input. So the important thing here is the set is going to be low dimensional. The set is going to be low dimensional. The size of set is going to be much, much smaller compared to the size of X. So so this is a way of reducing the dimension using in a completely unsupervised way. So what is the use of this? So once you have trained this model, let's say you have your input data, there is large number of unlabeled data, there's a small subset of labeled data. And you can train your autoencoder into your entire data set, even if it is unlabeled. And then what we will do is we will just discard the decoder. We don't need the decoder at all. And we will just take this encoder part. This much part we will take. And then the parameters of the encoder are already trained using the unsupervised learning. Now we just need to take the feature and maybe classify it, do whatever you want with it. For that, you can use the label data. But since the features are low dimensional, it's much easier to train this classifier, even using this less amount of label data. And this way, you can efficiently train your neural networks using much less number of examples. Okay. Now, what is variational autoencoders? Yeah. In variational autoencoders, it is basically you are just changing the autoencoder to get a generative model. Yeah. So what do I mean by this? Yeah. So you, in the SED, the latent vector that you get, you assume that there's a prior distribution. Yeah. So there's a distribution on the SED that you assume. Yeah. Now, then you will transform SED to X using a decoder, very similar to normalizing flows. Yeah. Except that we don't care now it is invertible or not. So question is how to train this model. Yeah. So this cannot be trained just like normalizing flows because the decoder need not be invertible. There's no restriction on decoder being invertible. Yeah. So we could write down the probability of the input image X. It will work out to be, you will need to, since the transformation from SED to X is not invertible, you will need to sum up over all the values of SED which result in X. You will need to add up all the values of SED which result in X, and you want to find the probability of all those things. Yeah? The thing is, this particular formula is very difficult to calculate. So you cannot do your optimization because there's an integral sign here. It's very difficult to calculate this particular formula. Yeah. So you cannot directly solve this problem. Yeah. So what people in VAEs do is, so this is an example of the encoder network. Yeah. So remember, so there's an encoder as well as decoder network. The encoder network, basically given the input, it instead of giving a SED, it will give you the mean as well as the variance values. Yeah? Because now SED is a random variable. It's a Gaussian distribution. So the encoder network predicts the mean as well as the standard deviation of the latent vector Gaussian. Yeah? And the decoder network, given the value C, it predicts again a Gaussian distribution, the mean and the standard deviation, for which the output is sampled from. Yeah? So it actually gives you the exact distribution of the output. So so this is an example of a VAE. So everything is sampled. It's an autoencoder, but instead of outputting the latent vector, it will output a distribution over the latent vector. Similarly, the decoder network will output a distribution over the output values, and not really a single output value. Okay, so I won't have time to describe this. So this is the loss function of a VAE. So there is something called a reparameterization trick, which allows you to train the VAE. So you can read up about it. Reparameterization trick. There's a reparameterization method which allows you to train VAE. And this particular quantity is called the elbow quantity, but this is always a number greater than or equal to 0. So this is ignored when you train a VAE. Yeah, so the loss function looks like this. And a part of the loss function is ignored. So you're not exactly training the VAE for the maximizing the probability, but whatever you're ignoring is a positive quantity. Yeah, so it is safe to ignore. So using this loss function, you can actually, so this is basically the loss function. Yeah. So this is your Lx theta phi. Okay. And using this loss function, you will sum up over the n images. So your input is x1 to xn. Yeah. So you try to maximize the parameters that maximizes the this loss function on this n examples. Okay, so that was VAE. And how do you generate data from a VAE? You sample your latent vector according to the normal 0-1 distribution, apply the decoder network, you get this the mean value and the variance of the output, and you sample from that. Yeah. So you will have a sample, but you also have the entire distribution of the output also if you want to do multiple samples. So the good thing about VAEs is now let's say you have some image and you have a latent vector which is 2-dimensional. Yeah. So this is the 2 dimensions you can vary. So you can vary Z2 and Z1, and nicely the images nicely sit, yeah, in a very nice order. All the ones towards the one side, zeros towards the one side. So this is a model trained on the MNIST data set, yeah, that is typically used in machine learning. Okay, yeah. So finally, coming to generative adversarial nets. So can it take 10 minutes more rather than the allotted time?
Yeah, sure, no problem. Yeah, sure.
So yeah, so I would like to cover this and also one example to physics, which might be more interesting to this crowd here. So yeah, so generative address. Yeah. So finally, I'm just covering the generative adversarial nets. It is slightly more complicated than the previous two, okay? In the sense that it's the training process is more complicated. It's little more difficult to understand, yeah, in some sense, but it gives the best results among all the methods. Yeah? So what is it? Yeah. So it's a very new approach. Okay, so this VAEs and even the normalizing flows was around for much earlier. Yeah, and GANs is a new approach. It was developed in 2014, 2015 time. So the idea is, so if you remember in VAE and normalizing flows, you are trying to maximize the likelihood, the probability of seeing the images in the data set. Now, we had to do a lot of workarounds to get there. Yeah? In normalizing flows, we had to have invertible mappings, yeah, to ensure that we can maximize the likelihood. In variational autoencoders, yeah, we had to say, okay, one quantity is negative, sorry, always positive, and we had to ignore that quantity. Yeah. So the GANs approach is, let's ignore the maximum likelihood. Maybe that is not the loss function we should maximize. Yeah? We should just try to make the samples that the model generates look similar to the actual data. If you cannot distinguish between the actual data and the examples generated by your model, then your model is good enough. Yeah, that is the broad idea behind GANs. Yeah? So how do you build a GAN? In GAN, there are two neural networks, two deep learning networks. One is called the generator, and another is called the discriminator. Yeah? So the generator is exactly like your decoder. Yeah? We saw decoders in normalizing flows and autoencoders, right? So it takes a latent vector, which is random noise, Gaussian distributed. It's a neural network which generates images from it. Yeah. So what does the discriminator do? Discriminator is again a neural network. Yeah. It basically looks at the fake images and the real images, and it tries to classify between these two. Yeah. So initially, so this generator network will have some parameter theta. The discriminator network will have some parameter phi. Initially, theta and phi are randomly initialized. Yeah. So what you will do is, initially the generator network will be generating some garbage because theta is randomly initialized. Yeah? But then you will train the discriminator network to classify between these fake and real images. Yeah? And in a few iterations, the discriminator network will learn to classify between them, because most likely this will be random noise, because the generator was randomly initialized. But once discriminator learns something, we will fix the discriminator and train the generator. Yeah, we will train the generator such that the distinguish will not be able to distinguish between these two. Yeah? So concretely, what happens? Yeah, so generator will try to fool the discriminator by generating real-looking images, and the discriminator will try to distinguish between real and fake images. Yeah? So there are two players. Yeah, there's a discriminator and the generator. Each person is trying to fool the other person. Yeah, so each person is like a neural network. Yeah, so if you look at this, X is sampled from P data. Yeah? That means it is from the real data. Yeah? And we would like the discriminator discriminator would like to say correctly on the real data that it is real data. Yeah. So you will maximize the parameter of theta d for log theta d, log d theta. So here the discriminator is trying to say the correct value. And when it is from the fake images, that is the generated images generated by generator is passed on to the discriminator. Yeah, we would like the discriminator to say the correct value. Yeah, so the discriminator would like to maximize, yeah, that it says the correct value, whether it is fake or real. That's what this particular area is saying. What the generator is trying to do is exactly the opposite. Yeah, it wants to minimize the situation that the discriminator can classify between real and fake. Yeah, so it's a min-max optimization. Yeah, and yeah, so basically the algorithm goes in 2 steps. Yeah? So for the discriminator, it will look at this loss function. Yeah? So this is the kind of the probability that the discriminator answers correctly. Yeah, this is the log probability discriminator is correct. Yeah, so the discriminator tries to maximize the probability that D is correct. Yeah, and yeah, using this loss function, it will learn something, and then you will stop the discriminator training. Yeah, and then you will start the generator training. What does the generator do? Generator will try to minimize the probability that the discriminator answered correctly. Yeah. Now, yeah, actually it should be minimization of this, but this quantity doesn't depend upon the discriminator. Sorry, the generator. So only this term depends upon the generator. So we can ignore this term and write this one. So in 2 steps, yeah, of 2 of the steps you can actually do yeah, training. So initially the discriminator learns to discriminate a bit. Then you stop the training of the discriminator. Then the generator tries to be smarter and fool the discriminator. So the generator has learned to fool the discriminator a little bit more. Now you again stop the generator. You start the discriminator training. Yeah, discriminator also learns to fool the little more smarter generator. So you are climbing a ladder. Yeah, so you have your discriminator here. You have your generator here. Initially, both of them are yeah, very stupid. You train a discriminator a bit. Yeah, so your discriminator learns something. Yeah, and using this discriminator, you will train this generator. So the generator learns something. Yeah, and using this generator, yeah, you will train the discriminator. So the discriminator learns something more. Using the little more clever discriminator, you will train the generator. Yeah, so all this keeps improving. So both of them keeps improving, and eventually you come to a state when both of them cannot improve anymore. Then you stop. Okay. So yeah, that's the broad idea behind GANs. And even though this looks like a very complicated idea, this seems to work really well, yeah, in practice. Yeah. So this is an example again from work with my student. Yeah. So there was this company who wanted to sort out bad quality seeds, corn seeds. Yeah. And some of the classes had yeah, very less number of annotated images. Yeah. So what we used is we used a GAN to generate images, yeah, for the classes which has very less number of examples. So these are images. One is real, one is fake. Can you distinguish? Tell me which one is real, which is fake? Yeah. So this is actually real, yeah, and this is actually fake. Yeah. So this is completely fake images generated by yeah, a generator model trained using the GAN. Yeah. And yeah, so even though we had very less amount of data, you could actually generate more data using a GAN and train a classifier, which gives improved accuracy. Yeah, so this was an application to yeah, actually sorting out corn seeds automatically, yeah, using machine learning. Anyway, so yeah, so I would like to give one final example quickly. of how it is actually being used, yeah, in the sciences. Yeah, I'm not sure it's a physics problem. It's possibly a problem in between physics and chemistry. Yeah. So this was in this paper. This is joint work with my fellow faculty at IIIT, Deva Priya. So essentially there was this materials data set. So there was a lot of materials with a lot of chemical formula is there. And you have some specific physical properties, yeah, which I will come to in a minute. And you would like to generate new materials, yeah, which has low specific heat, high conductivity, something like that. Yeah. You would like to find a material which has high value of certain physical properties. Now, you cannot, suppose your model tells you some 1,000 candidates. Yeah. Now it's you will have to finally verify whether those 1,000 candidates actually has good specific heat or good conductivity and everything. You have to do 1,000 experiments. Yeah. So you want to find out a algorithm which gives you a reasonable number of good quality candidates. Yeah, which has the properties that you need. Yeah. So the idea is, typically, there is a predictor model, and then you have some screening. There will be large number of candidates. This was the typical approach. Yeah. So we had another approach to it using variational autoencoders. Yeah. So what is our approach? Yeah. So first we will convert a chemical formula like this. We will take a chemical formula like this, and basically encode it into a matrix. You have to represent your thing into a matrix that can be fed into a machine learning model. Yeah. So we had an interesting representation. So your y-axis is all the elements, x-axis is the number of elements in that particular material. So basically you write down this matrix. Yeah. Most of it will be 0. Every row will have exactly 1, 1. So this is how you convert your input to the input to your machine learning algorithm. And what you do is we basically build a autoencoder. So it's a just as we described, it's a variational autoencoder. You have the input feature vector, but we also concatenate the material properties. So this material properties might be, I will come to in a minute what the specific properties are. Might be something like specific heat or some things like that. So you append that to that, and you have variational autoencoder which tries to recover the feature vector. And this is the unsupervised way we can easily learn this mapping. And it's a variational autoencoder. So your latent space has a probability distribution. It's a Gaussian density. Yeah. So the C here means conditional. Okay. So the difference between the earlier VAA and this is you will be also appending some additional material properties to the latent space. Yeah, that's the only difference. Okay. So so after we trained this variational autoencoder, we tried to analyze how the latent space looks like. Yeah. So we started with a point in the latent space, Z initial. So the Z initial corresponded to this particular compound. Yeah. And the Z final corresponding to this particular compound, this particular point. Yeah. And we tried to move along a line between this to this. And if you look at it, the intermediate compound that you see is kind of somewhere intermediate between this and this. For example, when I moved this way, you got another compound which is very close to this, but 1 element less. So it shows that the latent space is very smooth in some sense. Yeah. So we also had a predictor model. Yeah. So predictor model basically took this input representation and predicted the formation enthalpy, energy per atom, volume per atom. These quantities was predicted by the model. There was data available to train this predictor model. And how does the pipeline work? You will use your trained autoencoder, the variational autoencoder. You will sample a random normal latent vector. You will specify the material properties that you need. Suppose you want, material which has a high formation enthalpy, low energy per atom, high volume per atom. Okay, some numbers you give here. Yeah, this model will generate good candidate feature vectors for good candidates. Yeah, which might have this material properties. Yeah, and not just that, we can move around in this latent space. When we move around this latent space, we'll get more interesting candidates. Yeah, that have these material properties. And once we get some lot of generated feature vectors, we'll further filter the number of candidates using the previous predictor model. So remember, we already trained a predictor model also, which predicts these quantities. And so use the predictor model to compute these quantities all over again. So these are new compounds which might not be in the data set. So you need a predictor model to compute those quantities. And so then you kind of threshold and say, okay, only within this range we would like our output to be. So you kind of narrow down the materials which has this particular properties. Yeah. So yeah, that's all from that talk. I hope I gave an idea of the 3 basic methods. I can list out the references also and share the slides with you. If there are any questions, I can take.
Thank you. Thank you, Dr. Giris. It's a wonderful talk, actually, both coming with mathematics and then showing the details, how it implements and applications. So I will tell you more from my field of research, how it connects. But in one line, out of these 3 methods, 2 methods, the last 2, are heavily used in the field of particle physics nowadays. So it's one of the active field of research in this direction. So thank you so much. I have a couple of questions that again I will come at the end. Maybe from the audience. I can see one question from Tejaswini that can we use VAE, variational autoencoder, for image compression?
Yes. Yeah. So yeah, that's a very good question. Yeah. So I didn't list out all the application here. So if you remember, for example, it's actually, your autoencoder itself is kind of doing image compression in some sense. Yeah. Remember, Z is a low dimensional feature vector. Your X might have 1000 dimensions. Yeah. Your Z is only 50 dimensional. Yeah? And from Z, you can, so you are minimizing this loss function. That means you are recovering your X to some extent. Yeah. So you can store this Z instead of the X. So you are compressing your image X to your latent vector Z, right? So it's already compressing the input to a much smaller dimension. This directly applying will not give you exactly good compression ratios, but combined with other techniques in variational autoencoders, this is actually beating the state-of-the-art compression techniques. Yeah. Only problem it is getting difficult to implement is this neural networks are typically a little bit slow on normal computers. They need some specialized processing called GPUs to run, unfortunately. Yeah. So in normal computers, if you use this encoding, decoding, it will be a little bit slow compared to existing techniques.
One more question from Penil Kumar. He's asking that you discussed 3 methods, VAE, GAN, and normalizing flows.
Yes.
Which one is the best generative method?
So GANs in practice gives you the best quality outputs. Yeah. But as you see, the GAN training is a little bit complicated. You have 2 networks, discriminator, generator. You have to train discriminator first, then generator, then discriminator, and so on. So when you train this in alternatively, sometimes it happens very often that the training doesn't converge to some interesting result. So the training is highly unstable. So it's very, very difficult to train a GAN correctly. You need to have a lot of machine power. You have to little bit do trial and error and everything. You need some really good expertise to train GANs. for small models, you can do it easily, but yeah, for more complicated large images, high resolution images, it's very difficult. Compared to that, normalizing flow, yeah, normalizing flow has also its own challenges. But one place where normalizing flow shines compared to GANs is, remember, in normalizing flows, yeah, you know the exact probability of every input. Yeah, so you know the probability of every input value. Yeah, and you know the distribution exactly. You can sample from Px of x. You know the explicitly the distribution. You have a formula for it. Yeah, but in your GANs, you can only sample from Px of x. You don't know the exact distribution. Yeah? And in many cases, especially in physics, where you want to be interpretable, Professor Vineet gave a very nice talk in the beginning. So you want to be interpretable. You want to understand more what happened and everything. In that case, you also want to have a handle on the distribution, not just your a sample from the distribution. Yeah. So normalizing flows is typically used when you want it to be more interpretable. You want to analyze your results more. That kind of things you can do only with a normalizing flow. GANs only will give you a result. You have to be happy with that. Okay.
Okay, there is one more question. Asa Putna, is GAN useful for finding out material properties shown in your last example?
Yes, I mean, you could use, instead of a VA, you could use GANs. So there are papers which use GANs instead of variational autoencoders. There are papers which use normalizing flows. So I didn't list out all the papers. I will add more references and share the PPT. I will try to add more references. So, I mean, yeah, all of these methods are alternative methods to do it. Yeah, so for, I mean, we did some experiments, and in our experiments for this particular problem, this worked well, and we were satisfied with it. Yeah, there are other models as well. You can model it using GANs as well as also.
If you have any question, please use the raise hand button, or you can write in the chat box or Q&A box. Let's wait for others. So maybe I can ask my first question here, because you were discussing the last example. So in that example, you had a plot where you are discussing this latent space and Z initial to Z final, the way it curves down. Yeah, exactly. So my first question is that how you got this plot, like it depends on, I mean, how you define the Z initial and Z final and combine this with the material names. Like, is it like the additional layer that you attached through which you are making this conclusion?
Yeah. So, so this is the variational autoencoder. Yeah. So we trained this variational autoencoder completely first. Yeah. So we took some 2 random points in this latent space. We want to understand how the latent space looks like. Is it some reasonable continuous latent space? That's what we wanted to analyze. Okay. So we took some 2 points in this latent space. This point we passed it to a decoder, and yeah, this point generated this particular formula as the output.
Okay.
And set final was another point in the in the latent space that generated this particular compound in the output. Yeah. And then we just took a line. Yeah, just took a line through here, divided it into equal number of intervals. Yeah. So let's say divide this line into equal number of intervals. Yeah. And look and try to generate using this. What does the decoder give? Try to generate using this. Yeah. So this point gave this. This point gave this. This point gave this. This point gave this, and so on. Yeah. So, so what we can infer from this is, when we continuously change, well, let's say we take a convex combination of these 2 points. Yeah. You actually get compounds which are kind of intermediate to both the extreme ones.
Yeah, yeah, exactly.
What you expect in a continuous space. Yeah.
Yeah, yeah, right.
Yeah, so this is a very typical analysis that you do for these generative models. Yeah, to make sure that they are very well trained. So this kind of thing happens only if the generative models is very well trained.
Okay, good. No question till now. So maybe I can go to the second one. And that's on the GYAN, that's again that you said. I was just wondering, the training part, you had this one min function, another max function, and coming together in the loss function.
Yes.
So my first question is that you had this, you started with the, and how it starts. You start with discriminator, it stops, then you use the generation, right? The generative, and then again you do. Can I just quickly say, because it looks like, are you increasing the training data size also? Because you are generating fake images. I was just wondering whether data set is also getting increased. Things like that.
It's completely my mistake. I went over this really fast and didn't spend enough time on this. Yeah. So let me try to explain it more slowly. Yeah. So initially, so we only have a set of images. Okay. We don't have anything. We don't have any label data or anything. We have just a set of images. Yeah. You have X1 up to Xn or some set of images. Okay. And we would, let's say your data set is very small. Yeah, we would like to generate more images like this. Yeah, we would like to get some X prime n plus 1 to X prime capital N. You would like to increase the input data to a large number. Yeah. So hopefully we would like to generate more images which looks like this, which is indistinguishable from this. That's the idea.
Yeah.
So how to generate indistinguishable images? Yeah. So we will have a generator to generate indistinguishable images. Yeah. The generator, it will take a latent vector and generate this X primes. That is the plan. Yeah.
Yeah.
Now generator has some parameters theta. Yeah. Now how do I train this generator? Yeah. Now the earlier approaches was we will just look at the probability of this training data and try to maximize that and optimize the theta. Yeah.
Right.
So here the plan was, so that was a little bit complicated. This trying to find the exact probability of the training data was getting a very complicated. So the alternative approach, what was said is, yeah, let's introduce another network. So called a discriminator. Yeah. So discriminator has no useful purpose for your particular use case. Yeah, the discriminator is just introduced for the training of the generator.
Okay.
Yeah. So it is some additional thing that you introduce. Yeah. So what we just trait X. So it might take, you might give X or X prime as input to it. Yeah. Input might be X or X prime. It might be X or X prime. Yeah. So if X is given to it, it should say real. Yeah. The binary classifier essentially. Yeah. If X is given to it, that is from this region, from your actual data images are given, it should say real. If your images are going to be generated by the generator, then it should say fake. Yeah. That's the goal of the discriminator, to correctly discriminate between this real images and the fake images. Okay.
Right.
Yeah. So this is the log likelihood of a discriminator saying the correct answer. Yeah. So if X is sampled from your data, so this is the data. If X is sampled from your data, yeah, then the discriminator should say 1. Yeah. So we want to maximize the probability of that happening. So let's say d theta of 1 meaning it is real. Yeah. So we want to maximize that. Yeah. And if X is taken from the fake, so this is, let's say P said this is generated. Yeah. Then the generator should say it is fake. So this is this is saying it is real and this is saying it is fake.
Yeah.
Yeah. So the generator is applied on the generator. So initially both of the theta G and theta D are randomly initialized. Theta G is fixed. You are not going to change it. You are going to freeze it.
Okay.
Yeah. And we will try to improve theta d. So initially there is a theta g 1 and there is a theta d 1. This is frozen, yeah, and we will try to improve theta d. Okay, yeah, we just maximize this. So let's say theta d, the discriminator becomes slightly more improved, theta d2. Yeah, now I freeze theta d2. I don't change it. Yeah, now I will train the generator such that discriminator will not be able to distinguish between real images and the fake images, yeah, which correspond to minimizing this exact same thing.
Yeah, right, yeah.
But the thing is, this first term here, yeah, does not depend upon the generator parameters. Yeah, so we can just ignore that. You only take the second term.
Okay, yes.
Yeah. So now you fix the theta d and you improve the theta g, and theta g improves the little bit more. So far, okay.
So right. So in that case, now you have extended the data set, like you have generated few more data sample, or you have just reshuffled the data sample and come up with more fake data in that sense.
Yeah. So I mean, there are different approaches to it. One is you can, I mean, when you want to train the discriminator, you can ask the generator to sample something on the fly and apply the discriminator to it. You will freeze theta g, but you can just generate using the generator without changing theta g. So this can be used, but the only issue is you have to run both the networks together. Yeah. So it is computationally expensive. So sometimes what people do is they generate a lot of images using the generator and keep it there, and it's like a additional data for the discriminator. Yeah.
Okay.
But this data should be discarded when you go to the next level of this ladder.
Okay. Yeah, because that's optimized for other values of theta g, right? Yeah. Okay.
Yeah.
So that way, it will try to generate more data, fake data, but with the motivation that it should fool the discriminator, right? I mean, discriminator should not do the real and versus fake classification in a much better way.
Yes. So this is the probability that discriminator answers correctly on the fake image. Yeah. And the generator is saying, minimize the probability of that.
Yeah. So when should I stop at this level? I mean, when I should be happy with my fake data is fine with that.
Yeah. So we track this value, both these values, as we go up the ladder. Yeah.
Okay.
At some point, both of them will not be able to improve upon their values.
Okay.
So both of them are playing a two-player game. Yeah, it's a zero-sum game, in fact.
Theories which comes with some unknown particles. Okay. And these unknown particles are extremely difficult in real experiments because they might not have enough data. So what theory people will do is that we come up with fake data in simulation and do this classification, okay, the known versus unknown, and try to come up with new observables, some variables, which then we say to the experimenters, go and use this kind of observables, because they come up, they are definitely experiments have some limitations. So they will say that I don't have enough data to say that I have observed something new. But using that fake data in simulation, we can have some idea of what could be the signatures of the unknown. So there is this, that's why this Kyan has got huge interest in particle physics nowadays, because experiments and theoretical people both are using this in hand. So it's a very good, actually. That's why I was trying to understand more, because it's one of the field that people are working in our field.
Yeah, and in fact, physics people are using in much more interesting ways. So most of the physics data are not really images or things like that. So a lot of data is in graph form. So there's a
Yes.
graph neural network area entire.
Exactly.
And you have graph-based GANs, variational
Yeah, I
autoencoders,
have
all
done
those
some.
things.
Yeah, exactly. So I have done some this graph network because you have these informations of different particles and you need to combine. In experiments, you need to combination. So theoretically, we have some setup. So in that graph neural network, you can come up with better methods. So it has got applications. So thank you so much actually for both these three. So I had one. Okay. There's one more question. Is normalizing flows. Maybe you answered. So we had this several explainable machine learning frameworks. So is there any existing ones, or do you have some idea that these normalizing flows can also be make some explainable framework, part of explainable framework?
So the good thing about normalizing flows is one is you get the explicit probability distribution. Yeah. So you can do further analysis on the probability distribution. In GAN, you only get a single output.
Yeah.
You get a sample from the distribution. But yeah, so you can, depending upon the field, how the distribution is structured, you can do a interpretable analysis of that distribution. Secondly, so the normalizing flows is invertible. You can go the latent vector and come back to the image also. Yeah. So now you can go to the latent vector space, do some modification there. Yeah. And for example, some of the things that we did was actually interpretability analysis. So the example that we saw here, this is actually interpretability analysis.
Yeah, exactly.
You are taking a latent vector and trying to modify it, and see if it corresponds to some particular thing in the image. So you are able to say, okay, this particular thing in the latent vector corresponding to this particular thing in this complex image. Yeah. So this is actually giving you an interpretable model, this normalizing.
And then you are tuning this, right, to get this younger and older version. So you know exactly where to tune in so that you get this. Yeah, that's true. So in that sense, this normalizing flows method is more closer to build a interpretable framework, right, than GAN or others.
Yes. It is more, it is more amenable to interpretability analysis compared to GANs. But the thing is, so normalizing flows has its own problems with training. So we cannot, very large data sets, we have been able to fit this faces data set, but these are only small images, okay, 200 pixel by 200 pixel or something. GANs can generate 1,000 pixel images, but this has not been able to scale to that extent. Also, the algorithms are a little bit slow. The inverse parse in a normalizing flow is not, it is a slow algorithm. One pass, one direction. So in GAN, it's basically just executing neural network. You don't need to invert the neural network in a GAN. You just need to run neural network, which is extremely fast, optimized. But in normalizing flows, you have to invert the neural network. Now, the inverse of the neural network is not, there's no efficient algorithm for it. And it's an open problem people are proposing. In fact, our work that we did, we were actually proposing a more efficient normalizing flow where the inverse is slightly improved, but not as good as GANs.
Okay, maybe last question. I got one from Professor Vijay Kumar Parmar. Which conditions or factors are very important for Z initialize to reach Z final? I think he's referring to that in the plot. Which conditions or factors are very important?
So, again, as we said, the idea is if we are variational autoencoders is trained really well, you take any 2 points in this latent space, and take a convex interpolation. That means you draw a line between these 2 points. As you move through this line from this point to this point, the generated molecules also will vary very nicely between the extremes, just like we saw in the images, right? So we varied the age parameter and it nicely varied between an old lady and a young lady. this is again the same thing happening for the molecules. Yeah, you are taking 2 points in the latent space and going in that direction, then it smoothly interpolates. So for a very well trained VA, no matter which 2 points you take and do this interpolation, the output generated molecules also should also be smoothly varying, yeah, from one extreme to the other. It is for any 2 points, it should be true for a well-trained VA.
Okay, I think we have no more questions. Okay, again, before we close this session, thank you so much, Dr. Girish, for this very beautiful talk, elaborative and informative both way. And
Thank you very much.
we look
I
forward
hope
to
I
having
could visit your university
Yes,
sometime. But
exactly. So we will plan for some visit for you to have more discussion on the campus. And so we'll contact you for other requirements. And of course, if we had some physics discussions, that will also be nice if you have free time. With that, we will close this session. We will start again the afternoon session from 2. And this time we will have talks on 2 areas in physics, one from particle physics and another from statistical physics. The speakers will discuss applications of deep learning methods in these 2 areas. Okay, so we'll meet at 2. And bye from my side and my colleague, Dr. SmoothGrad. We'll meet again at 2. Thank you so much. And thank you, Dr. Girish, once more.
Thank you. Bye.
Bye.
Thank you.